Ever wondered how long it would actually take to reach every planet we know, in real time, days, years, or lifetimes? From the worlds closest to us like Venus and Mars, to the frozen giants on the edge of our solar system, and then far beyond into the endless sprawl of the Milky Way, the actual time it takes to travel between them will blow your mind. Stay tuned, because we're about to leave Earth behind and find out what it really means to travel across the galaxy. This is What's the Actual Time It Takes to Reach Each Planet in the Milky Way? The scale of the impossible. You've probably seen those beautiful images of the solar system, a neat row of planets, evenly spaced, looking like neighbors who could wave to each other if they wanted. But that's the biggest illusion in science, because those planets are nowhere near each other. They're not sitting in a straight line. They're floating in a black ocean so wide, so quiet, that the distances between them can't even be drawn to scale without making Earth smaller than a grain of dust. When you look at a space map, everything feels reachable. You can see Mercury, Venus, Mars, all laid out in order, just like subway stops. But if you actually tried to travel to them, you'd realize something shocking. You could fire the fastest rocket humans have ever built, and you'd still spend months, even years, just getting to the next dot on that map. The truth is, those charts lie to you in the same way a globe lies about the size of the continents. They make space look small enough to fit inside your imagination. But the reality, it doesn't fit anywhere. The moon, which feels close enough to visit in a weekend trip, is still 384,000 kilometers away. That's almost 10 times the distance around the planet. And even at rocket speed, it takes about 3 days just to get there. 3 days to move a single pixel on the cosmic map. So let's be real. Space isn't about distance, it's about time. Because in the void, speed is everything. Distance doesn't mean much when your fastest ships crawl through space slower than a snail on a football field. The only real way to measure space travel, the only thing that makes sense, is how long it takes. Think of it like this. Imagine walking to your neighbor's house. 10 minutes, maybe 15. Now imagine that same walk but across a desert that never ends, where you can't breathe, where the horizon never gets closer. That's what moving between planets is like. Every step forward takes hours, days, months. Every mile is a lifetime. But we forget that because movies made it look easy. You've seen it. Spaceships darting between planets in seconds, astronauts landing on Mars after a short nap, ships reaching other galaxies before the popcorn runs out. But that's fiction. In the real world, nothing in space is fast. Even the speed of light, which feels infinite, isn't enough to conquer how large our galaxy really is. Let's slow down for a second. When scientists talk about how far things are, they use words like kilometers, astronomical units, and light years. Sounds technical, right? But here's what they really mean. A kilometer is the distance you could drive in less than a minute on a highway. It's what you use on Earth. But in space, kilometers are useless. The numbers get too big, too fast. So instead, astronomers use something called an astronomical unit, or AU. That's just the average distance from Earth to the Sun, about 150 million kilometers. That's how far light travels in about 8 minutes. Now that's just to the Sun. Mercury orbits much closer. Neptune, the farthest planet, orbits about 30 AU away, 30 times the distance between Earth and the Sun. So when you think of Neptune, you're not thinking millions of kilometers. You're thinking billions. And that's only our solar system. Beyond that, the numbers start breaking your brain. 1 light year, the distance light travels in a year, is about 9.5 trillion kilometers. Light, moving at 300,000 kilometers per second, needs a whole year just to get that far. So when we say our nearest star, Proxima Centauri, is 4.24 light years away, what we're really saying is this. If you could somehow move as fast as light itself, it would still take you over 4 years to reach the next closest star. And no, we can't go that fast. Not even close. The fastest human-made object ever launched is the Parker Solar Probe. It moves at about 700,000 kilometers per hour. That's fast enough to circle Earth in less than a minute, but still only 0.064% of light speed. If you used that probe to travel to Proxima Centauri, it would take you over 7,000 years to get there. And yet, we still dream about going farther. That's what makes this question so fascinating. Not just how far each planet is, but how long it would take us to actually reach them. What would that journey look like? What would it feel like to travel for months just to see a red dot become a world? Or to drift for decades past the edge of the sun's light? Because when you think about it, every destination in space is time-based. To reach Mercury, you need patience. To reach Mars, you need courage. To reach the outer planets, Jupiter, Saturn, Neptune, you need faith that you'll still be alive to see them. And to reach beyond, into the darkness where the stars themselves are the next stop, you need something more than technology. You need the kind of endurance humanity has never known. Every spacecraft we've ever built, everyone has only just begun to scratch the surface of our own backyard. Voyager 1, the farthest human object ever, has been flying since 1977. It's been moving at over 17 kilometers per second for more than 40 years. It's already left the solar system. And yet, it hasn't even traveled 1 light year, not even one. That's the scale we're talking about. The universe isn't measured in miles or kilometers, it's measured in moments. It's measured in every second that passes while a spacecraft burns fuel, coasts in silence, and keeps moving through nothingness. Every second in space is time stretched thin, and every planet we reach is another reminder of how fragile our speed really is. If you left Earth right now, heading straight into the unknown, you wouldn't just be traveling through space. You'd be moving through time, slowly, endlessly, painfully, counting years like miles and realizing that even the smallest steps forward can take generations. This is what we're about to explore, not just the map of planets, but the clock that rules them. How long it truly takes to reach every world we can see, and even the ones we can't. Because in space, the finish line isn't where you think it is. It's further, always further. Leaving Earth sounds simple. You light the engines, point up, and go, leaving Earth as the launch pad. But the truth is, escaping our planet isn't about height. It's about speed. Every step you take, every object you drop, every plane that flies, all of it is ruled by gravity. And you need to outrun it. That's what scientists call escape velocity, the speed you need to be traveling before Earth's gravity stops pulling you back. It's not about thrust, or distance, or altitude, it's all about momentum. Once you hit that speed, you're gone. It takes about 11.2 kilometers per second. That's roughly 40,000 kilometers per hour. To put that in perspective, if you fired a bullet straight up, it would travel at maybe 1 kilometer per second before slowing down and falling back to the ground. A fighter jet moves at less than 1 kilometer per second. A commercial airplane, maybe 0.25. That means to leave Earth, you need to move more than 40 times faster than a speeding bullet. That's escape velocity, the invisible finish line that separates the atmosphere from everything beyond. It's one of those numbers that sounds simple on paper, but is brutally hard in practice. Because getting to that speed isn't like flooring a car on an empty road. You're dragging a massive machine upward through thick, resisting air, carrying tons of fuel, fighting both weight and wind. Every extra kilogram makes the climb harder. Every second you're slower than 11.2 kilometers per second, gravity is clawing you back down. That's why rockets look the way they do. Huge, loud, and mostly full of fuel. In fact, about 90% of a rocket's mass at launch is fuel. The spacecraft itself, the part that actually goes to space, is usually just a small capsule sitting on top, riding a controlled explosion out of the atmosphere. The challenge is pure physics. The more fuel you carry, the heavier you are. But the heavier you are, the more fuel you need to lift that extra fuel. It's a vicious loop. One that engineers have been trying to outsmart for decades. When a rocket launches, it's not going straight up into space like a dart. It tilts slightly as it climbs, curving its path until it's almost moving sideways. That's not a mistake. It's on purpose. The goal isn't to go up, but to go fast enough sideways that as you fall toward Earth, the ground curves away beneath you. That's what orbit really is. You're falling, but you never hit the ground because the planet keeps curving out of your path. Once you reach orbit, you've escaped the pull just enough to circle the Earth forever. But escaping completely, heading to the Moon, Mars, or beyond, that takes even more speed. You need to accelerate past orbital velocity, past gravity's grip, until the Earth finally lets you drift into the emptiness of interplanetary space. That's where the real journey begins. Let's compare this to something familiar: airplanes. When you look out the window on a flight, you might feel like you're already in space. The sky turns dark, the curve of Earth appears faintly below, and the world feels far away. But you're barely scratching the surface. Commercial planes cruise at about 900 kilometers per hour. That sounds fast, until you realize the International Space Station orbits Earth at 28,000 kilometers per hour. That's 31 times faster than your plane, and that's still not escape velocity. The station doesn't leave Earth's pull, it just keeps falling around it in a perfect loop. To actually leave Earth completely, you'd have to go even faster. Faster than any jet engine or turbine could ever push. That's why rockets exist. Chemical rockets, the kind we use now, are basically giant controlled explosions. They burn fuel at incredible temperatures, forcing gases out the back to push the rocket forward. The science behind it hasn't changed much since the early days of space travel, only the precision and efficiency. Back in the 1960s, during the space race, NASA's Saturn V rocket was the most powerful machine humans had ever built. It stood 363 feet tall and could produce 7.5 million pounds of thrust. That was enough to lift 3 astronauts, their lunar lander, and all their supplies toward the Moon. When Apollo 11 launched in July 1969, it took just 12 minutes to reach orbit. 12 minutes to climb from sea level to the edge of space. That's the power of escaping Earth. But even then, they weren't done. They still had to ignite another stage of the rocket to push their speed higher, up to that magic 11.2 kilometers per s, to break free entirely and begin the 3-day coast to the Moon. So how fast were they really going? The Apollo astronauts reached about 39,000 kilometers per hour, barely over the line. Just enough to escape. Once they were free, gravity from the Earth and Moon balanced out, and the spacecraft drifted smoothly toward its destination. Decades later, rockets have become smarter, safer, and slightly more efficient, but not that much faster. The physics hasn't changed. SpaceX's Falcon 9 rocket, for example, still relies on chemical combustion. It's brilliant in engineering, capable of reusing its boosters and cutting costs drastically, but its top speeds in orbit aren't drastically higher than Apollo's. Falcon 9 can push payloads into orbit at around 27,000 kilometers per hour, just enough to stay up there. If it's launching an interplanetary mission, the upper stage might reach speeds closer to 40,000 kilometers per hour to escape Earth completely. But the real advances come not from getting faster, but from getting cheaper and more repeatable. Each new rocket launch brings us closer to a time when space travel isn't rare, but routine. Still, no matter how efficient we make the engines, we keep hitting the same wall. Gravity doesn't change, and fuel only burns so fast. To understand just how limited we are, let's step back and look at our fastest travelers. After the Apollo missions, NASA launched the Voyager probes in 1977, small robotic explorers designed to visit the outer planets and then drift into interstellar space. Voyager 1 used Jupiter's gravity as a slingshot to gain speed, reaching a record-breaking 62,000 kilometers per hour relative to the Sun. For decades, it held the title of the fastest human-made object ever launched into deep space. Even at that speed, though, Voyager 1 would need over 70,000 years to reach the nearest star. That's how massive the scale of space really is. Then came the Parker Solar Probe, launched in 2018, built to study the Sun up close. As it falls closer to the Sun's gravity, it accelerates to insane speeds, over 700,000 kilometers per hour. That's about 200 kilometers per second. If it were flying around Earth, it could circle the planet in under a minute. That makes Parker the fastest human-made object in history. But even at that unimaginable speed, it would still take more than 6,000 years to reach Proxima Centauri. That's the cruel math of space. The distances grow faster than our speed ever could. When you see rockets launch on TV, they look smooth and graceful, a bright column of fire rising into the sky. But inside, it's chaos. Tremendous vibration, crushing G-forces, temperatures beyond what most metals can handle. Every piece of the rocket is fighting physics to stay alive for just a few minutes. Once it burns enough fuel to lighten its load, it starts to accelerate faster and faster, climbing through the thinning air until the sky goes black. At around 100 kilometers above sea level, the Kármán line, the rocket is officially in space. But it's still nowhere near free. It needs to keep firing, keep pushing, until it's going fast enough sideways to stop falling back. When that happens, it's finally orbiting. From that moment, everything changes. The engines cut off, and suddenly, silence. No wind, no drag, no up or down. The capsule is weightless, drifting, circling the planet once every 90 minutes. You can see the curve of Earth glowing blue and white below. The sun rises and sets 16 times a day. It's both beautiful and terrifying, because it's only then you realize how fragile that line between up here and down there really is. But orbit isn't freedom, it's captivity with style. You're still tethered by Earth's gravity, just moving fast enough that you never fall. To truly leave, you need another burst of speed. That's why spacecraft headed to Mars or the outer planets always fire an extra engine burn, the transorbital injection, to escape completely. Once that happens, you're no longer Earth's property. You're on your way, and this is where the idea of time starts to hit. Every journey from here on is measured in months, years, or even decades. You can't just go somewhere in space. You drift, you coast, you wait. The engines that got you out of Earth's pull are done, their fuel spent. All that's left is momentum. A tiny ship gliding through nothing, carrying everything it needs to survive. Every spacecraft we've launched started with that same first step, beating gravity. It's the hardest, most expensive part of the whole journey. Once you're free, everything else is just distance and patience. The Apollo missions taught us how to escape. The Voyagers taught us how to keep going. The Parker Solar Probe taught us that even at unimaginable speeds, we're still moving painfully slow compared to the universe. When we look at Earth from above, it's easy to feel small. But when you look at what it takes to leave it, the energy, the precision, the speed, you realize how powerful we've already become. We've built machines that can break free from a planet's grip. Machines that can run for decades without stopping. Machines that have already crossed into the space between stars. Mercury, the inner sprint. Now, if space travel were a race, Mercury would seem like the easiest lap. It's the closest planet to us on average, only about 77 million kilometers away. On paper, that sounds almost next door compared to Jupiter or Saturn. But that's the trap. Mercury might be close in distance, but in space travel terms, it's one of the trickiest destinations to actually reach. You see, distance in space doesn't behave the way we imagine it on Earth. You can't just point your rocket at Mercury and floor it like you're on a galactic highway. The moment you leave Earth, you're still under the influence of the Sun's gravity, and that's where everything gets complicated. To reach Mercury, a spacecraft has to slow down, not speed up. That's the first mind-bending truth about visiting the innermost planet. Because Earth orbits the Sun at around 30 kilometers per second, any spacecraft leaving Earth already carries that sideways speed. To drop towards Mercury, you have to cancel much of that momentum, like slamming the brakes on a cosmic racetrack where there are no brakes. And that's what makes Mercury so deceptive. You'd think going inward, closer to the Sun, should be easier than flying outward to Mars or Jupiter. But to fall inward, you have to shed enormous amounts of orbital energy. If you don't, you'll just zip past Mercury and keep looping around the Sun forever, missing it again and again. That's why reaching Mercury isn't a sprint. It's more like trying to roll a ball down a steep hill while slowing it just enough so it doesn't fly off the edge. Let's imagine it this way. You're standing on a carousel spinning fast. You want to move toward the center, but as you try, the spinning motion keeps pushing you outward. The faster the spin, the harder it is to get close to the middle. The Sun's gravity works in a similar way. The planets are all moving around it at huge speeds. The closer to the Sun, the faster the orbit. Mercury screams around the Sun at nearly 47 kilometers per second. That's the fastest orbiting planet in the solar system. To catch Mercury, you have to match that orbital speed at just the right time and angle. That's like trying to merge onto a racetrack where everyone is doing 170,000 kilometers per hour and you're joining from a side road, but with no brakes, no tires, and no pit stops. When NASA first tried to visit Mercury in the 70s, engineers quickly realized this wasn't going to be like Apollo or even the Mars missions. The first spacecraft to attempt it was Mariner 10, launched in 1973. Instead of going straight for Mercury, Mariner 10 took the scenic route, flying past Venus first. That wasn't a detour, it was a clever use of gravity assist. A gravity assist works like this. The spacecraft swings past a planet, letting that planet's motion sling it in a new direction while also changing its speed. For free. It's like stealing a bit of the planet's momentum. Mariner 10 used Venus to slow itself down just enough to fall closer to the Sun. Without that trick, it would have never reached Mercury at all. It finally made it there in March 1974, about 5 months after launch. Not bad by today's standards, right? But here's the catch. Mariner 10 didn't stay, it just flew by. 3 times actually. Each time it snapped photos and collected data before zooming away again. It didn't have the fuel to slow down enough to orbit Mercury. The mission gave us the first real look at Mercury's cratered surface. A world that looked eerily like our moon, baked by the sun and nearly airless. But it also showed just how hard it would be to ever stay there. It would take more than 30 years before humanity tried again. In 2004, NASA launched Messenger, a more advanced spacecraft designed to finally orbit Mercury. But even with better technology, this mission wasn't fast. Messenger didn't arrive at Mercury until 2011, almost 7 years later. Why so long? Because to reach Mercury, it couldn't take a direct route. The spacecraft had to perform 6 gravity assists, 1 around Earth, 2 around Venus, and 3 around Mercury itself, before it could finally slow down enough to be captured by Mercury's gravity. 7 years to travel 77 million kilometers might sound ridiculous. You could cross the entire solar system faster than that if you went in a straight line. But that's not how orbital mechanics work. You're not driving across empty space. You're surfing a sea of invisible gravity wells. You can't just push straight through. You have to move with the currents. Messenger's patient dance paid off, though. Once it arrived, it became the first spacecraft ever to orbit Mercury. It spent 4 years mapping its surface, discovering ice hidden in its craters, and finding evidence that the planet wasn't as dead inside as we thought. When it finally ran out of fuel in 2015, Messenger plunged into Mercury's surface, a controlled crash that ended one of NASA's most intricate missions. Our most recent traveler toward Mercury is Bepi Colombo, a joint mission between the European Space Agency and Japan's space agency, JAXA. Launched in 2018, it's actually 2 spacecraft traveling together, one built by ESA to map Mercury's surface and magnetic field, and one by JAXA to study its inner structure. But again, the timeline shows how tough Mercury really is. Bepi Colombo is scheduled to finally reach Mercury's orbit in 2025, 7 years after launch, just like Messenger. Along the way, it's making 9 flybys. 1 of Earth, 2 of Venus, and 6 of Mercury itself. Each pass fine-tunes its path, shaving off speed bit by bit. Every time it swings by Mercury, it lets the planet's gravity slow it down, like tapping the brakes without burning precious fuel. So even in 2025, with all our advanced science, reaching Mercury still takes years. Not because it's far away, but because it's trapped deep inside the Sun's gravitational grip. To really appreciate how slow our fastest missions are, let's put it in perspective. If you could somehow travel to Mercury at the speed of light, which is about 300,000 kilometers per second, you'd get there in just 4.3 minutes. That's shorter than a commercial break. But our rockets, they're nowhere near that fast. The Parker Solar Probe, the fastest human-made object ever built, reaches speeds of about 700,000 kilometers per hour, roughly 0.064% of light speed. At that rate, you could reach Mercury in about 5 days if you went in a straight line with no slowing or speeding needed. Of course, reality is crueler. Because of gravity and orbital alignment, no one's doing that. The real-world missions take years. Mariner 10 takes 5 months, flyby. Messenger is 6.6 years, orbit. Bepi Colombo is 7 years, orbit, projected. That's not a race, that's a marathon through molasses. Here's where it gets even crazier. Mercury is the closest planet to every planet in the solar system, on average. That's because it hugs the center of the solar system, while all the other planets swing wide arcs around the Sun. But closest doesn't mean easiest. It's like living next to the base of Mount Everest. Sure, it's nearby, but reaching the top is another story. That's why Mercury remains so mysterious even today. We've sent dozens of missions to Mars, landed rovers, even flown helicopters there. But Mercury? Just a handful of flybys and 1 orbiter. It's small, scorched, and hard to reach. The cosmic equivalent of a hot coal sitting at the bottom of a deep well. Movies have spoiled our sense of scale. When we see spaceships darting between planets in seconds, it feels normal. But even Mercury, the closest of all, reminds us how slow we really are. Every mission that's reached it had to use years of planning, precision, and patience. Each one fought against the pull of the Sun, burned tons of fuel, and still moved slower than a snail compared to light. In a way, Mercury is humbling. It sits there, right next to us, glowing faintly in the early morning sky. A reminder that in space, close doesn't mean easy, and fast is still painfully slow. If it takes us 7 years to reach the nearest planet inward, what happens when we go the other way, toward Mars, Jupiter, or even Neptune? Venus, our hellish twin. On paper, Venus is our twin, nearly the same size, almost the same gravity, made of rock, wrapped in a thick atmosphere. But take one step into that atmosphere, and everything we know about Earth-like turns into a nightmare. Venus isn't just hot, it's lethal. The temperature on its surface is over 460 degrees Celsius. That's hot enough to melt lead. And the pressure is about 90 times what you'd feel on Earth. That's the same crushing force you'd experience a kilometer under the ocean. The clouds that look so beautiful in pictures, they're not fluffy white cotton. They're made of sulfuric acid. Yet despite its danger, Venus has a strange pull on scientists. And for good reason. It's the closest planet to Earth. Sometimes it's closer than Mars ever gets. At its nearest point, Venus can be just 38 million kilometers away, half the distance to Mars. So close that it's often the brightest object in the night sky, outshining every star. But close in astronomy doesn't mean easy. Getting there is quick, but surviving there is another story. Let's start with a fun fact. Venus is technically our closest planetary neighbor on average, not Mars, not Mercury. Depending on where the planets are in their orbits, Venus and Earth can be on opposite sides of the Sun, or nearly touching shoulders across the cosmic street. When both are aligned perfectly on the same side of the Sun, a position called inferior conjunction, they're only about 38 million kilometers apart. Mars, even at its very closest, never gets nearer than about 55 million kilometers. So, if you're talking about pure distance, Venus is the easiest trip. That's why, in the early days of space exploration, scientists targeted it right after the Moon. It was close enough to reach quickly and, they hoped, might even resemble Earth in more than just size. They were wrong about that last part. The fastest trip humanity has ever made to another planet was to Venus. Back in 1962, NASA's Mariner 2 launched toward the planet and arrived just 4 months later. 4 months. That's insanely quick in space terms. For comparison, most missions to Mars take 7 to 9 months. Messenger took 7 years to reach Mercury. So when you realize Mariner 2 pulled off the Venus trip in just 109 days, it feels almost impossible. But that short time came with some big catches. First, it was a flyby. No orbit, no landing, just a high-speed drive-by snapshot. The spacecraft zipped past Venus at nearly 35,000 kilometers per hour, gathered what data it could, and kept going. Still, what it discovered changed everything. Until Mariner 2, we didn't know what was happening beneath Venus's thick clouds. Many scientists actually thought it might be a lush tropical world, a warm version of Earth with jungles and oceans hidden by haze. Mariner 2 shattered that fantasy. Its instruments revealed surface temperatures of nearly 900 degrees Fahrenheit, 475 degrees Celsius. Hotter than Mercury, even though Venus is twice as far from the Sun. The atmosphere. 96% carbon dioxide, dense enough to trap heat in a runaway greenhouse effect. That discovery was a turning point in planetary science. Venus wasn't a paradise, it was a warning. The planet that could have been Earth's twin had become a furnace, a world cooked by its own atmosphere. One of the biggest misconceptions people have is that Mars is right next to us. Pop culture loves to talk about colonizing Mars, sending humans there, turning it green again. Venus rarely gets that kind of spotlight, even though on paper it's a much shorter trip. Here's why. Venus's orbit is inside Earth's, closer to the Sun. That means the time it takes to reach Venus depends on where both planets are positioned in their elliptical dance around the Sun. About every 19 months, Venus comes to its closest point, a moment astronomers call inferior conjunction. During that time, it's practically within cosmic touching distance. Mars, on the other hand, orbits farther out. Even at its closest point, the trip takes longer, the energy requirements are higher, and the alignment window is narrower. So why don't we send more missions to Venus? Because close doesn't mean safe. The challenge isn't getting there, it's what happens when you arrive. The Soviet Union learned that the hard way. Between 1961 and 1984, they launched a series of spacecraft under the Venera program, more than a dozen attempts to study Venus. Most failed spectacularly. Some burned up in the atmosphere, others lost communication before they even arrived. But a few succeeded, and what they found was terrifying. Venera 7, launched in 1970, became the first spacecraft to land on another planet and transmit data back to Earth. It survived for 23 minutes before melting. The temperature readings it sent home confirmed everything Mariner 2 had suggested. Venus's surface was a living inferno. Later missions like Venera 13 in 1982 sent back the first color photos from the surface. The landscape looked alien and bleak, cracked, orange-brown ground under a thick, yellow haze. The atmosphere was so dense that the parachutes meant to slow the lander's descent were barely needed. The air itself was like liquid. If you could somehow stand on Venus, your lungs would collapse instantly, your skin would blister in seconds, and your equipment would fail almost immediately. Even today, no lander has survived longer than about 2 hours on Venus. Despite all that, Venus remains the fastest destination we've ever reached. Most missions, depending on the alignment, take 4 to 6 months to get there. Let's break down a few real examples. Mariner 2, 1962, is 4 months. Fastest trip ever to another planet. Magellan, 1989, is 15 months. It took a longer, fuel-efficient route to enter orbit. Akatsuki 2010 is Japan's first Venus mission, supposed to arrive in 2010, but due to a propulsion failure, it missed orbit and spent 5 years looping around the Sun before finally entering orbit in 2015. That's space travel for you. A mix of precision and patience, where a single malfunction can turn a few months' journey into half a decade. Even though Venus is relatively close, space agencies often use it as a stepping stone instead of a destination. Why? Because Venus is perfect for gravity assists. Those slingshot maneuvers that help spacecraft gain or lose speed without using extra fuel. For example, the Galileo mission to Jupiter in the 1990s used a flyby of Venus and 2 of Earth to build up enough velocity to reach the outer solar system. The Messenger mission to Mercury also swung past Venus twice on its way inward, using its gravity to slow down. Venus's position near the Sun makes it an ideal pit stop in the cosmic racetrack. If you plan your trajectory right, Venus can either catapult you outward toward Mars and Jupiter, or pull you deeper inward toward Mercury and the Sun. It's like the ultimate interplanetary roundabout, if you can handle the heat. Now, what if we had better engines? Ones that could ignore fuel limits and push straight for Venus without worrying about orbital alignments. How fast could we really get there? Let's imagine a few scenarios. At the speed of light, the trip would take just 2.1 minutes. That's shorter than the time it takes to brush your teeth. You could literally blink, and you'd be there. At Parker Solar Probe's speeds about 700,000 kilometers per h, the trip would take roughly 2 days, still mind-blowingly fast compared to current missions. At SpaceX, Falcon, heavy speeds around 40,000 kilometers per h. It would take 80 days, less than 3 months. That's almost realistic, though we're still limited by fuel and orbital paths. So theoretically, Venus could be the most reachable planet in our entire solar system. But as of now, getting to Venus is the easy part. Surviving on Venus is the impossible part. But you may ask, what makes Venus so dangerous? Venus is what scientists call a runaway greenhouse planet. Billions of years ago, it might have looked a lot like Earth. It may have had oceans, clouds, and a stable atmosphere. But over time, volcanic eruptions released massive amounts of carbon dioxide. The gas trapped heat, which caused more water to evaporate, which trapped even more heat. Eventually, the cycle spiraled out of control. The oceans boiled away, the atmosphere thickened, the planet's surface baked under an eternal pressure cooker of CO2 and acid clouds. It became a living warning of what happens when a planet's climate goes rogue. Today, the air is so thick it bends light. The sun would look like a dim orange glow behind clouds that never clear. If you dropped a steel wrench on the ground, it would corrode before it cooled. That's why every Venus mission is unmanned. Even the toughest robotic landers can't handle it for long. Still, scientists haven't given up on Venus. In fact, in the next few years, we're going back. NASA's upcoming Veritas and Da Vinci Plus missions are planned to launch in the late 2020s. They'll map Venus's surface in incredible detail, searching for signs that it might once have been habitable, or that volcanic activity is still reshaping it today. Why bother studying such a hostile world? Because Venus could hold the key to understanding our own planet's future. It's a mirror of what could happen if Earth's climate ever spiraled out of balance. By studying Venus, we're not just learning about another world, we're protecting our own. Venus is our closest neighbor, the easiest to reach, and yet it remains the least explored of the inner planets. We can land rovers on Mars and send probes to Jupiter, but Venus keeps its secrets hidden behind that thick, poisonous veil. Every time we try to get closer, it burns us. Still, the temptation is too strong. It's so near, so bright, it feels like it's calling us back. And maybe one day, when propulsion tech evolves beyond chemical rockets, when we can fly with ion drives, nuclear engines, or even solar sails, Venus might finally give up her secrets. Until then, she remains the beautiful killer of the solar system, our hellish twin, always close enough to see, but too deadly to touch. If reaching Venus in just 4 months already sounds fast, wait until we set our sights outward, to Mars. A planet that's twice as far, colder than Antarctica, but somehow feels more alive in our imagination than any other. Mars, humanity's first destination. For decades it's been the dream. The red planet, dusty, distant and mysterious, has captured our collective imagination like no other world in the solar system. From the first telescope sketches in the 1800s to today's billion-dollar rockets and robotic rovers, Mars has become more than just a point of light in the sky. It's humanity's next great frontier. Every time you see a photo from NASA's rovers, the endless orange deserts, the mountains that stretch under a salmon-colored sky, it feels strangely familiar. It looks like somewhere we could go, somewhere we should go. But here's the truth. Mars isn't close. It's far. So far that even at our fastest, most efficient speeds, getting there is a half-year journey across the void. A trip that tests not only our technology, but the limits of human patience, psychology, and endurance. Let's break down what it actually takes to reach the planet that could become our second home, and why, even with rockets roaring and billionaires racing, Mars still feels like the edge of forever. The first thing to understand about Mars is that it's never in the same spot relative to Earth. Both planets orbit the Sun, but at different speeds. Earth makes one lap every 365 days. Mars takes 687. So sometimes we're on the same side of the Sun, close together. And sometimes we're on opposite sides, separated by more than 400 million kilometers. When both planets are perfectly aligned, what astronomers call opposition, the distance between Earth and Mars can shrink to about 55 million kilometers. That's the sweet spot for launching missions. It happens roughly every 26 months, and that window only stays open for a few weeks. Miss it, and you'll have to wait more than 2 years for another chance. At its farthest point, Mars can be about 400 million kilometers away. That's more than 7 times the close approach distance, meaning any spacecraft headed there outside the ideal window would need massive amounts of fuel, time, and luck. That's why every Mars mission, from the first flybys to the rovers we see today, has been carefully timed to match this cosmic alignment. In space travel, timing isn't just important, it's everything. So how long does it actually take to get to Mars? The short answer, anywhere from 6 to 9 months, depending on when you leave and how fast you go. The longer answer depends on a specific type of trajectory called a Hohmann transfer orbit. Think of it as the most fuel-efficient path between 2 orbits. Instead of traveling in a straight line, spacecraft take a long, looping curve, using the Sun's gravity to sling them from Earth's orbit to Mars's. It's like tossing a ball at just the right angle so it lands perfectly in a moving basket millions of kilometers away. Here's what that's looked like in practice. Mariner 4, 1964, took 228 days, that's about 7.5 months, the first successful Mars flyby. Viking 1, 1975, took 304 days, the first successful landing on Mars. Mars Reconnaissance Orbiter, 2005, took 210 days. A modern, high-speed mapping mission, Perseverance rover, 2020, took 203 days, NASA's most advanced rover yet. These durations line up with what we can expect from chemical rockets, the same basic propulsion method we've been using since the dawn of the space age. Even at their peak, these rockets only reach speeds of about 25,000 kilometers per hour leaving Earth. That's blistering fast by human standards, but still painfully slow in the scale of space. At that speed, it's like driving around the Earth's equator every hour for 8 months straight. If getting to Mars were as simple as go straight, we'd be there all the time. But space travel is all about alignment. Because both Earth and Mars are constantly moving around the Sun, any spacecraft must aim for where Mars will be, not where it is. Launch too early or too late, and you'll miss the target by millions of kilometers. That's why the launch window to Mars comes only once every 26 months, when the planets line up just right. During that time, spacecraft can use minimal fuel to slingshot toward Mars using the Sun's gravity as a helper. The rest of the time, the geometry of the orbits makes the journey incredibly inefficient. You'd either have to go much faster, which takes enormous fuel, or travel on a long looping path that could take over a year. This delicate play is one reason Mars missions are so expensive and so rare. Every opportunity counts. When the window opens, everything, every calculation, every booster, every valve, has to work perfectly. There's no second try until 2 years later. No conversation about Mars would be complete without mentioning Elon Musk. For nearly 2 decades, he's been promising to take humanity to Mars through SpaceX, the company that's revolutionized rocketry and made space cool again. Musk's vision is bold: establish a self-sustaining city on Mars within our lifetimes. He said the first crewed Starship missions could happen in the late 2020s. But how realistic is that? Let's look at the details. SpaceX's Starship rocket is the most powerful launch vehicle ever built, fully reusable, with a theoretical payload capacity of up to 100 tons to Mars. It's designed to refuel in orbit, allowing multiple ships to stack energy before heading off together. On paper, that sounds perfect. Musk's plan involves launching fleets of Starships during every Mars window, around every 26 months, carrying cargo, equipment, and eventually, people. But reality hits hard when you look at the timeline. To date, no Starship has completed an orbital mission, let alone a full interplanetary flight. The logistics of refueling in orbit, protecting passengers from cosmic radiation, and ensuring reliable life support for 6 months in deep space are still largely theoretical. Even with SpaceX's incredible progress, the idea of sending humans to Mars by the late 2020s is optimistic, to put it gently. Realistically, we're likely looking at the mid-2030s or later for a crewed mission, assuming everything goes right. And even then, it won't be a quick trip. Starship's journey time will still hover around 6 months, maybe 4 with the most efficient burns. Musk talks about faster travel, but until we move beyond chemical propulsion, those limits won't change much. So what if we didn't rely on chemical rockets at all? What if we use something faster, smarter, maybe even futuristic? That's where ion propulsion and nuclear thermal engines come in. Ion propulsion works by accelerating charged particles, ions, to extreme speeds using electricity. It produces very little thrust, but it can run continuously for months, gradually accelerating the spacecraft to massive velocities. NASA's Dawn spacecraft, for example, used ion engines to visit 2 asteroids, Vesta and Ceres, over nearly a decade of travel. It wasn't fast, but it was incredibly efficient. In theory, an ion engine powered by nuclear or solar energy could cut the Mars trip time dramatically, down to about 70 to 90 days. Then there's nuclear thermal propulsion. Instead of burning chemical fuel, it uses a nuclear reactor to heat hydrogen, ejecting it at much higher speeds. The concept dates back to the 1960s, when NASA's NOVA program successfully tested prototypes. Modern designs suggest a nuclear-powered rocket could cut the Mars trip to 3 to 4 months, depending on the route. That's a game changer. Faster trips mean less radiation exposure, less food to carry, fewer psychological risks for astronauts, and more frequent launch opportunities. NASA and DARPA are actually working on a nuclear thermal demonstration mission, DRACO, planned for launch around 2027. If it works, it could pave the way for the first rapid Mars missions in the 2030s. Still, theoretical doesn't mean tomorrow. These systems need rigorous testing to ensure they're safe, not just for astronauts, but for Earth itself. Launching nuclear material into orbit isn't exactly something you rush. Think about what those 6 to 9 months actually mean for the humans who'll one day make the trip. Imagine being sealed inside a spacecraft for 200 days straight. No fresh air, no gravity, no real sunlight, just the endless hum of life support systems and the black silence of space outside. You can't open a window, you can't go outside. Every breath you take is recycled air. Every sip of water is purified waste. The only view is the tiny red dot of Mars slowly growing in the distance. Astronauts on the International Space Station already face similar isolation, but they're just 400 kilometers from Earth, a phone call away, a supply ship away. On the way to Mars, you'll be tens of millions of kilometers away, with a delay of up to 22 minutes for a single radio message to reach home. If something breaks, you can't turn around. If someone gets sick, there's no emergency return. That's why the travel time isn't just a technical challenge. It's a human one. Every extra day in transit adds psychological strain, radiation exposure, and logistical complexity. Cutting that time down even by a few weeks could make the difference between life and death on a mission. After months of quiet flight through space, the real danger begins when you arrive. Landing on Mars is one of the hardest engineering problems humanity has ever faced. Its atmosphere is only 1% as thick as Earth's, too thin to slow a spacecraft down with parachutes alone, but too thick to ignore entirely. It's the worst of both worlds. NASA calls it the 7 minutes of terror, the time it takes for a spacecraft to go from interplanetary speed to safely landing on the surface. At entry, the vehicle hits the atmosphere traveling over 20,000 kilometers per hour. There's no chance for human correction. By the time mission control gets word it's entering, it's already over, one way or another. That's why every Mars mission is packed with redundant systems, heat shields, parachutes, and retro thrusters that have to work in perfect sync. Even then, the odds are brutal. Of all missions ever sent to Mars, over 50, roughly half have failed. That's the graveyard you join when you aim for the red planet. But when it works, it's breathtaking. From Viking to Curiosity to Perseverance, each successful landing is a triumph of human precision. A 200-day gamble ending in a 7-minute heartbeat. Why Mars? Why spend billions, risk lives, and wait months for a journey that could fail in seconds? Because Mars is the first world that feels reachable. It's close enough to visit, familiar enough to study, and, maybe one day, livable enough to settle. It has water ice. It has days that last 24.6 hours. Its gravity is light, but not zero. It's not a gas giant, not a toxic inferno, not a frozen wasteland like Pluto. It's something in between, a planet that whispers, you could live here. That's why Musk dreams of it, why NASA plans for it, and why every spacefaring nation has its eyes on that red horizon. But even with all our ambition, all our rockets, and all our money, Mars reminds us how small we still are. 6 months of travel, in silence, in darkness, through invisible radiation, just to reach a place where survival lasts minutes without a spacesuit. It's humbling, it's terrifying, and it's exhilarating, because it proves that when humanity sets its eyes on something far, we don't stop, we just build better engines. Let's imagine, for a moment, that the limits are gone. No fuel worries, no orbital alignment, just raw, unrestricted speed. If you could travel at the speed of light, Mars would be only 3 to 22 minutes away, depending on where the planets are in their orbits. That's the delay time NASA deals with when sending commands to rovers. And it's also a reminder of how slow we are compared to the universe's ultimate speed limit. At Parker Solar Probe speeds, 700,000 kilometers per h, you could reach Mars in about 33 days at the closest approach, a little over a month. At nuclear thermal speeds, let's say 100,000 kilometers per h, you'd arrive in about 23 weeks, 5 months. That's half the time of our current missions. But to do better than that, we'd need propulsion methods that border on science fiction. Fusion drives, antimatter engines, even light sails powered by lasers. Theoretical? For now, yes. Impossible? Not at all. Human history is a pattern of turning the impossible into Tuesday's test flight. So we've crossed 55 million kilometers to reach a planet that's just barely hospitable, where each mission takes nearly a year from launch to landing. That's Mars, the nearest place we can imagine living outside Earth. And yet, it's only the beginning. Because once you look past Mars, the distances explode. The travel times stop being months. They become years. The fuel required becomes unthinkable. Beyond Mars lies the asteroid belt, then the gas giants, Jupiter and Saturn, followed by the frozen worlds of Uranus and Neptune, and finally, the icy fringes of the solar system. Reaching those worlds makes Mars look like a weekend road trip. If Mars is humanity's first destination, those outer planets are our test of endurance, our leap into true interstellar travel. So as incredible as it is to stand on the red sand in your imagination, the farther you go, the slower time seems to move, and the more space stops being about distance and becomes entirely about time. Jupiter, the giant gateway. There's a moment somewhere past the orbit of Mars when the Sun starts to look small, not like a blazing disk, but a fierce, distant star. The warmth fades, the light dims, the silence becomes thicker, heavier, colder, and then in that endless night it appears. A swirling, banded titan, larger than life and brighter than anything else in the sky. Jupiter. It's not just another planet. It's a world so massive that if it were 80 times larger, it would have ignited into a star. It's the gatekeeper of the outer solar system, a cosmic fortress of storms, radiation, and raw gravitational power. Every mission that goes beyond Mars must first reckon with Jupiter's influence. Some use it as a slingshot. Others are caught in its pull, but no one ignores it. Jupiter isn't just a planet, it's a gateway. Getting to Jupiter isn't a quick trip. In fact, by the time you arrive, the spacecraft you launched from Earth is already a veteran of space. At its closest, Jupiter is about 588 million kilometers away from Earth. At its farthest, it can be over 970 million kilometers. For comparison, that's roughly 5 to 9 times the distance to the Sun. To get there, you're not just crossing space, you're crossing into a different kind of solar system. The average travel time for a spacecraft to reach Jupiter is between 5 and 6 years, depending on the trajectory and propulsion technology used. That may sound long, but when you consider the immense distances involved, it's actually remarkably fast. Let's look at some real examples. Pioneer 10, 1972. The first spacecraft to reach Jupiter took about 21 months, just under 2 years, to get there, arriving in December 1973. Voyager 1, 1977, took about 1 year and 9 months to reach Jupiter, arriving in March 1979. Galileo, 1989, launched by Space Shuttle Atlantis, took over 6 years, arriving in December 1995. New Horizons, 2006, is the fastest launch ever from Earth. It reached Jupiter in just over 13 months en route to Pluto. Juno, 2011, took 5 years, arriving in July 2016. So why the difference? Why can one spacecraft arrive in just over a year, while another takes 6? It all comes down to energy and how much of it you're willing or able to spend. In space, speed comes at a price. To reach Jupiter directly, you need an enormous amount of energy to escape Earth's gravity, then accelerate enough to climb the Sun's gravity well all the way out to the 5th planet. Most missions can't carry that much fuel. It would make the spacecraft too heavy to launch. So instead, engineers use gravity assists, clever maneuvers that steal a bit of momentum from planets along the way. You launch toward one planet like Venus or Earth, swing around it, and use its gravity to gain speed and change direction. It's like using the planets themselves as giant slingshots. The Galileo mission, for example, didn't fly straight to Jupiter. It took a looping route: Earth, Venus, Earth, Jupiter. Those gravity assists saved enormous amounts of fuel, but stretched the travel time to over 6 years. By contrast, New Horizons was built for raw speed. It didn't carry much fuel and didn't need to break into orbit around Jupiter. It just used Jupiter's gravity as a boost toward Pluto. That's how it covered nearly 800 million kilometers in barely a year. It's the difference between driving economically and drag racing. One conserves energy, the other burns everything for speed. Jupiter's defining feature isn't its size or its storms, It's its gravity. This planet has a gravitational pull 2.5 times stronger than Earth's. It's so powerful that it doesn't just control its own moons. It shapes the entire outer solar system. Asteroids that might have crashed into the inner planets are often deflected or captured by Jupiter's massive gravity field. Many scientists believe Earth owes its habitability partly to Jupiter acting as a cosmic shield, sweeping away dangerous debris. But for spacecraft, that gravity can be both a gift and a curse. When used correctly, it's a gateway, a source of free energy. Missions like Voyager, Cassini, and New Horizons use Jupiter's gravitational pull to gain thousands of kilometers per hour in speed, flinging them towards Saturn, Uranus, Neptune, and beyond. Voyager 1, for instance, reached 61,000 kilometers per h relative to the Sun after its Jupiter encounter, fast enough to become the most distant human-made object in history. But Jupiter's gravity can also trap you. To slow down enough to enter orbit, a spacecraft must burn a massive amount of fuel to fight against the planet's pull. That's what made Juno's arrival so dramatic. As it approached in July 2016, the spacecraft fired its main engine for 35 minutes, a single critical burn that had to be perfect. Too short, and it would slingshot past Jupiter forever. Too long, and it would dive into the planet's atmosphere, never to be seen again. It was a razor's edge, but it worked. Juno slid into orbit at nearly 209,000 kilometers per hour, becoming the first spacecraft to orbit Jupiter since Galileo. For most of human history, Jupiter was just a bright dot in the night sky, a shimmering, mysterious world with faint stripes seen through telescopes. That changed in March 1979, when Voyager 1 flew past. For the first time, we saw Jupiter up close. Its endless belts of clouds, its great red spots swirling like a storm the size of 3 Earths, and its moons, each one a world of its own. Voyager 1's footage was breathtaking. It revealed volcanic eruptions on Io, cracked ice plains on Europa, and mysterious dark streaks on Ganymede. These weren't dead rocks. They were dynamic living systems. Just 4 months later, Voyager 2 followed, giving humanity a second, more detailed look before continuing towards Saturn. Together, the Voyagers transformed our understanding of the outer planets. Every image they sent home made Jupiter seem both terrifying and mesmerizing. A world of storms and radiation, but also a beacon of possibility. Voyager had given us a glimpse, but it was just a flyby. To truly understand Jupiter, we had to stay. That's where the Galileo mission came in. Launched in 1989, it took more than 6 years to reach Jupiter, finally arriving in December 1995. Once there, it became the first spacecraft to orbit the gas giant. Galileo spent 8 years studying the planet and its moons. It sent back over 14,000 images and uncovered some of the most astonishing discoveries in space exploration. One is Europa. It has a subsurface ocean beneath its icy crust, possibly twice the volume of all Earth's oceans combined. Io is the most volcanically active body in the solar system. Ganymede, the largest moon in the solar system, has its own magnetic field, something previously thought impossible for a moon. Galileo also dropped a small probe into Jupiter's atmosphere in 1995, which transmitted data for nearly an hour before being crushed and melted by the immense pressure and heat. The data it sent back showed winds reaching 600 kilometers per h, temperatures of 700 degrees Celsius, and pressures hundreds of times stronger than anything on Earth. The probe was obliterated, but in doing so, it told us more about Jupiter's depths than we'd ever known. After years of service, Galileo was intentionally plunged into Jupiter's atmosphere in 2003 to avoid contaminating any of the icy moons. It ended its mission the way so many great explorers do, by diving into the unknown. Fast forward to 2011. NASA launched Juno, a solar-powered spacecraft on a 5-year voyage to Jupiter. Unlike Galileo, which ran on nuclear power, Juno relied on 3 giant solar panels, each the size of a semi-truck. It was the farthest any solar-powered spacecraft had ever traveled. When it arrived in July 2016, it entered a highly elliptical orbit designed to skim close to Jupiter's poles, then swing far out to avoid the most intense radiation zones. What Juno found was staggering. The spacecraft revealed that Jupiter's famous bands of color extend thousands of kilometers deep, not just surface clouds. Its Great Red Spot, a storm that's been raging for centuries, is hundreds of kilometers deep and shrinking slowly over time. Juno also discovered powerful auroras at the poles far stronger than any on Earth, generated by Jupiter's massive magnetic field, which is 20,000 times stronger than our planet's. The data Juno continues to send has rewritten textbooks, showing that Jupiter is far more complex, turbulent, and mysterious than we ever imagined. Its imagery, especially those captured by JunoCam, are breathtaking. Swirls of blue, green, and cream, like oil on water, constantly shifting in motion. Its chaos and beauty in equal measure. Jupiter's gravitational influence stretches across the solar system. It's what scientists call a gravity well, a measure of how much energy it takes to escape an object's gravity. Jupiter's gravity well is so deep that once you fall into it, it's extremely hard to leave. That's why spacecraft must perform huge burns to enter or exit orbit. For example, if a spacecraft were to drop straight toward Jupiter from far away, it would accelerate to over 200,000 kilometers per hour by the time it reached the cloud tops. Escaping again would require the same amount of energy, more than what's needed to leave the entire solar system from Earth. This immense gravity is both a barrier and a tool. It can hinder travel, trapping spacecraft or pulling them into destructive orbits, but it can also aid travel, slingshotting them toward the outer planets with incredible efficiency. Without Jupiter's gravity assists, missions like Voyager, Cassini, and New Horizons would have taken decades longer, or required far more fuel than we could ever carry. Jupiter, in that sense, is the solar system's launch pad to the stars. So what happens when we start to build faster, more advanced spacecraft? Could we cut the 5-6 year journey to Jupiter down to 1? 6 months? Even less? In theory, yes. But it depends on the propulsion technology. First is ion propulsion, electric drives. Using continuous low-thrust acceleration, an ion-powered spacecraft could reach Jupiter in roughly 2 to 3 years. It would start slow, but gradually build immense speed over time, saving huge amounts of fuel in the process. Second is nuclear thermal rockets. With double the efficiency of chemical rockets, an NTR system could reach Jupiter in about 14 to 18 months, roughly a quarter of current travel times. Third is nuclear electric propulsion. This hybrid concept, combining nuclear power with electric thrust, could, in theory, get to Jupiter in under a year. It's not yet possible with today's materials and power systems, but it's within the realm of 21st century engineering. Fourth is fusion propulsion. Still theoretical, but if fusion drives ever become reality, they could push a spacecraft to Jupiter in weeks. That's the promise of engines like the Daedalus or Helios fusion concept, near light-speed bursts of acceleration that would make the solar system feel small. Imagine leaving Earth in January and reaching Jupiter by March. It sounds like science fiction, but so did walking on the moon once. Speed and gravity aren't the only challenges. Jupiter is surrounded by one of the most dangerous radiation environments in the solar system. The planet's magnetic field traps charged particles from the solar wind, creating enormous radiation belts, far more intense than Earth's Van Allen belts. These zones can fry electronics, damage spacecraft, and pose serious risks to any humans who ever venture that far. Juno, for instance, was designed with a titanium vault around its core systems to protect them from radiation. Even so, its electronics will gradually degrade the longer it remains in orbit. For human missions, Jupiter is currently off-limits. Any crewed spacecraft would need shielding equivalent to several meters of lead, completely impractical with current technology. That's why, for now, we send machines instead of people. Machines don't fear radiation, they don't need air, and they can survive long enough to show us what's waiting out there. Beyond Jupiter lies everything else. Saturn, Uranus, Neptune, Pluto, and the Kuiper belt. Every mission that has gone beyond the asteroid belt has passed by Jupiter first. It's the gravitational crossroads of the solar system, the planet that makes deep space exploration possible. Without Jupiter's gravity assists, Voyager wouldn't have reached Saturn, Uranus, or Neptune in a single lifetime. Without Jupiter, New Horizons would have taken twice as long to reach Pluto. Even future missions to the outer moons or the edge of the solar system, like a potential Europa Clipper or the proposed interstellar probe, will rely on Jupiter's power to fling them outwards. It's fitting that Jupiter, the mythological king of the gods, still rules the heavens, not through lightning, but through gravity. If you were to stand on one of Jupiter's moons, say Europa, and look up, you'd see a sky dominated by a striped giant filling half the horizon. Lightning storms would flash across its surface, the great red spot would swirl like a living eye, and somewhere tiny and blue in the distant black would be Earth. That's what Jupiter reminds us, how far we've come, and how much farther there still is to go. It's the giant gateway, the threshold between the inner worlds we know and the frozen frontier beyond. Saturn, the jewel of the sky. If Jupiter is the gateway, then Saturn is the cathedral. Even through a telescope, Saturn doesn't look real. It floats in the dark like a god's ornament, wrapped in shimmering rings that stretch hundreds of thousands of kilometers into space, each one made of glittering ice and rock. You've heard about it your whole life, but nothing prepares you for seeing it. It's the most beautiful thing in the solar system, and yet, one of the most distant places humanity has ever reached. By the time you get here, you've traveled more than 1 billion kilometers from home. Saturn orbits the Sun at an average distance of about 1.4 billion kilometers, almost twice as far as Jupiter. And in the emptiness of space, that difference is staggering. Every extra step outward takes exponentially more time, more energy, and more patience. Light itself takes over an hour to travel from the Sun to Saturn. For a signal from Earth, it's a round trip of nearly 3 hours. That means if you sent a command to a spacecraft there, you wouldn't even know if it received it until almost 2 hours later. Cassini, NASA spacecraft launched in 1997, didn't reach Saturn until 2004, 7 years later. 7 years of silent drifting through the void, powered by nothing more than gravity assists and nuclear batteries. It flew past Venus twice, looped around Earth, then swung by Jupiter before finally catching up with its destination. Think about that. A spacecraft traveling tens of thousands of kilometers per hour using the most advanced navigation systems we had still took 7 years to get there. That's how slow we move compared to the scale of space. By the time Cassini arrived, it had already traveled 3.5 billion kilometers, looping, adjusting, slingshotting through the solar system like a cosmic marathon runner. When it finally entered Saturn's orbit, scientists and engineers around the world cried tears of joy. Imagine waiting 7 years just to reach the starting line. And then imagine what it must have felt like to see those first high-resolution images come through, the rings glowing, the planet's shadows slicing through them like a blade of light. For the first time, humanity was close enough to see Saturn's storms swirl in real time, massive cyclones, polar hexagons, and lightning bolts thousands of times stronger than any on Earth. It was like peering into another dimension. Saturn moves slowly, completing one orbit around the Sun every 29.5 Earth years. It spins fast though, one rotation every 10.7 hours, flattening it at the poles and stretching it at the equator. You can see that bulge even in pictures. Everything about Saturn is extreme, yet graceful. Its rings, while vast, are paper-thin, only about 10 meters thick in some areas. From up close, they look solid, like a smooth sheet of ice, but they're actually made up of countless particles, from tiny grains to house-sized boulders, all orbiting in perfect harmony. When Cassini flew between those rings, it was a ballet of timing and luck. One wrong trajectory, and the probe would have been shredded by debris traveling faster than bullets. The distance to Saturn, plays tricks on your sense of scale. We think in terms of minutes or hours, maybe days. But out here, everything is measured in years. At the speed of the fastest jet on Earth, it would take more than 150 years to reach Saturn. Even a commercial airplane traveling non-stop at 900 kilometers per hour would need over 150,000 hours, or nearly 2 decades, to make the trip. Our fastest spacecraft ever, the Parker Solar Probe, would still need almost 4 months at top speed if it could go in a straight line. But nothing travels straight in space. Every move must respect gravity, momentum, and fuel efficiency. That's why Cassini's 7-year journey was actually the fastest possible with the technology we had. And yet, for all that distance, Saturn has become one of the most studied planets in history. Cassini spent 13 years orbiting it, mapping its moons, diving through its rings, and capturing more than 450,000 images. It discovered that some of Saturn's moons, especially Enceladus, have geysers shooting water vapor and ice into space, hinting at oceans beneath their frozen surfaces. It found that Titan, Saturn's largest moon, has lakes of methane and ethane, rivers flowing under thick orange haze, and a climate that mirrors Earth's in bizarre alien ways. Every discovery made the long wait worth it. But every image also reminded us how much farther we still have to go. Saturn challenges everything we know about time. Imagine being born when a spacecraft leaves Earth for Saturn, and only being in high school by the time it arrives. Imagine being part of the mission team, watching your creation drift across space for nearly a decade, unable to touch or fix it, praying that it survives the radiation, the cold, and the sheer emptiness of its path. The patience required for space exploration isn't human, it's cosmic. Out here, success demands that we slow down, that we accept the universe moves at its own pace, and that progress is measured in light hours, not miles. When Cassini's mission finally ended in 2017, it went out in one of the most poetic ways imaginable. NASA sent it diving into Saturn's atmosphere, where it burned up like a falling star. They called it the grand finale. As it descended, Cassini kept sending back data until the very last second, studying the planet it had orbited for over a decade. Then the signal faded, and silence returned. 20 years after launch, humanity's connection to Saturn's explorer was gone. But in that silence, there was something beautiful, the realization that our reach, however slow, now extended to a world more than 1 billion kilometers away. If we could build faster ships, that silence might not last so long. Imagine a future where nuclear thermal propulsion becomes reality, where a spacecraft could reach Saturn in just over a year, or a fusion-powered vessel, cutting that to mere months. Engineers already dream of ion drives powered by reactors that could push us at constant acceleration, reaching outer planets without the long waits or gravity assists. In theory, if we could sustain 1/10 the speed of light, the trip to Saturn would take under 2 hours. It sounds impossible now, but so did airplanes, satellites, and moon landings once upon a time. That's the beauty of Saturn. It forces us to dream bigger. Every mission to it, every photo of those rings is a reminder that we're capable of touching the unreachable, even though we can't stand on its surface, because there is no solid surface. The fact that we've studied its storms, mapped its moons, and understood its rhythm means we've already claimed a small part of it. It belongs to human curiosity now. Saturn's moons are like an entire miniature solar system. Titan, with its dense atmosphere, could hold secrets about life's chemistry. Enceladus, with its hidden ocean, might already harbor microbes swimming in the dark. Rhea, Dione, and Iapetus each hold mysteries of their own. Cassini showed us that these aren't just rocks orbiting a gas giant, they're worlds in their own right. And the more we saw, the more we realized how small Earth really is in the grand design. Think about the patience it takes for sunlight to even reach Saturn. Over an hour just to cross the void, the same light that takes 8 minutes to touch Earth's oceans. That means when you look at Saturn through a telescope, you're not seeing it as it is. You're seeing it as it was over an hour ago. Out there, even time moves differently. When scientists say Saturn is 1.4 billion kilometers away, what they're really saying is that Saturn exists 1 hour in the past, always just beyond our present. And that's what makes it so hypnotic. Every planet we've passed so far, Mercury, Venus, Mars, Jupiter, all seem close compared to this. Saturn is the first time you feel like you've left the Sun's neighborhood entirely. The warmth fades. The light turns gold, then pale, then silver. The stars start to dominate the sky. Space becomes colder, emptier, and yet somehow more beautiful. If Jupiter is the edge of what we can imagine, Saturn is the beginning of what we can't. Cassini's cameras captured auroras at Saturn's poles. Glowing, ghostly curtains of light twisting through an atmosphere made mostly of hydrogen and helium. They pulse like heartbeat rhythms from a world that shouldn't even have one. These auroras, caused by Saturn's magnetic field interacting with solar wind, are hundreds of times stronger than Earth's. It's almost like the planet is alive, breathing in the solar wind and exhaling light. And as your spacecraft drifts through the shadow of those rings, looking back at the sun's faint glow through their icy arcs, you finally understand why space isn't measured in kilometers or even years. It's measured in awe. Because no matter how fast we go, no matter what propulsion we invent, the scale of this journey will always make us feel small. Saturn teaches us patience, but also perspective. It reminds us that we're explorers in an ocean of time. When Cassini took its final image of Earth, a tiny blue dot nestled between the rings, it didn't just show how far we'd come. It showed how much farther there is to go. Billions of kilometers behind that dot, other people who built the machine, the people who dreamed of this moment, and the generations who'll one day travel even farther. And while 7 years might sound like a lifetime, in cosmic terms, it's nothing. The planets have been orbiting for billions of years, waiting patiently for us to catch up. Each time we send a new mission, we're adding one more heartbeat to the rhythm of discovery that started the moment we first looked up. But here's the twist. Saturn isn't the end of our solar neighborhood. It's only halfway out. Beyond it lie Uranus, Neptune, and the icy frontier of the Kuiper belt. Uranus, the forgotten frontier. Only one spacecraft has ever visited Uranus. Just one, Voyager 2, the lone traveler that left Earth in 1977 and became humanity's first and last visitor to this strange frozen world. It took 8.5 years to get there. 8.5 years of coasting through black space, past Jupiter and Saturn, gathering momentum from their gravity and heading deeper into the cold. When Voyager 2 finally arrived in January 1986, Earth was listening. Billions of miles away, a faint radio signal brought back images that stunned the world. Uranus wasn't what scientists expected. From Earth, it had always looked featureless, a smooth, unbroken orb of pale cyan. But Voyager's close-up pictures revealed subtle clouds, faint rings, and something even stranger. The entire planet was tilted on its side. Unlike any other world in the solar system, Uranus spins almost horizontally, like a rolling ball instead of a spinning top. Its axis is tilted 98 degrees, meaning its poles take turns facing the sun directly for decades at a time. One half of Uranus bakes in continuous sunlight, while the other half freezes in endless night. And then, after 42 years, they switch. The cause of that tilt is one of space's great mysteries. Most scientists believe that billions of years ago, Uranus was struck by a planet-sized object, a collision so massive it knocked it over and changed its entire orientation. Imagine a world getting hit so hard, it never stands upright again. That's Uranus. A silent reminder of how violent the early solar system really was. The journey to get there, though, is just as mind-bending. When Voyager 2 left Earth, Jimmy Carter was still president. The first Star Wars movie had just premiered. People were still typing on manual typewriters. By the time it reached Uranus, the world had changed. Kids who were born the year it launched were in middle school. Technology had evolved, Nations had shifted, and yet Voyager was still out there, faithfully transmitting data from 3 billion kilometers away. The light from Uranus took nearly 3 hours to reach it. That means every signal, every command, had a 6-hour round-trip delay. When Voyager 2 snapped its first photos of Uranus, those pictures had to crawl through interplanetary space for hours before anyone saw them. When they did, the world was speechless. Uranus looked serene, almost painterly. Its soft cyan hue came from methane in its upper atmosphere, which absorbs red light and reflects blue-green. But beneath that calm face lies a violent heart. Winds on Uranus can reach up to 900 kilometers per hour, faster than the strongest hurricanes on Earth. Its atmosphere is a mix of hydrogen, helium, and methane, and deep below, it's believed to hide an icy mantle surrounding a rocky core. But the term ice giant doesn't really do it justice. The temperatures there can drop below minus 220 degrees Celsius. If space feels cold, Uranus is what cold aspires to be. And then there's its magnetic field, tilted, lopsided, and completely offset from its core. Unlike Earth's magnetic field, which is neatly aligned with our rotation, Uranus's is skewed by almost 60 degrees. The result is a magnetic bubble that wobbles wildly as the planet spins, creating auroras that dance unpredictably across its surface. When Voyager passed by, scientists could barely make sense of it. It was as if the planet's magnetic field had been twisted by the same mysterious impact that knocked it on its side. But perhaps the strangest thing about Uranus isn't its tilt or its cold, it's how little we know. Voyager 2 spent only 6 hours in the planet's vicinity, 6 hours after an 8.5-year journey. It flew by, snapped a few pictures, took a few readings, and then moved on. No orbit, no return trip, just a fleeting glance before it disappeared into the dark. Since then, no spacecraft has ever gone back. No follow-up mission, no close-up photos, nothing. For almost 40 years, Uranus has been sitting out there, alone, silent, waiting. Every other major planet has been revisited. Jupiter's had multiple missions. Saturn had Cassini. Mars has become practically a tourist destination with rovers and orbiters. Even tiny Pluto got its moment in 2015 when New Horizons gave us a glimpse of its frozen plains. But Uranus? Still forgotten, still waiting for someone to care enough to return. Part of the reason is distance. Saturn is already 1.4 billion kilometers away, but Uranus is almost twice that, nearly 3 billion kilometers from the Sun. The farther you go, the slower everything becomes. Solar power weakens, radio signals fade. The temperature drops to levels where metal becomes brittle and machinery must fight to stay warm. Missions to Uranus are not impossible, just expensive, complex, and brutally long. Even with the best gravity assists and current propulsion, a new probe would still take over a decade to get there. But that's the thing about Uranus. It quietly mocks our limits. It reminds us that the solar system isn't small. It's vast beyond imagination. If you tried to drive there in a car going 100 kilometers per hour, it would take over 3,000 years. If you could fly there in a fighter jet, it would still take hundreds of years. And even at the speed of light, you'd need 2 hours and 40 minutes just to get there. That's how remote Uranus is, a world so far away it exists almost outside of time as we experience it. And yet, despite being so distant, Uranus plays a crucial role in the architecture of our solar system. Its gravity shapes the paths of icy bodies that drift in the outer reaches. It anchors the balance between the inner worlds and the far frontier. It's also a glimpse into what most planets in the galaxy probably look like. Astronomers now believe that ice giants like Uranus are among the most common types of planets in the Milky Way. That means understanding Uranus isn't just about studying one planet, it's about understanding billions of them. In the decades since Voyager 2's visit, scientists have proposed countless missions to go back. Orbiters, probes, even flybys with improved technology. None have been approved yet. Funding, timing, and competing priorities always seem to push Uranus to the background. It's the quiet student at the back of the class, overshadowed by flashier siblings. But recently, interest is growing again. NASA's planetary scientists have identified Uranus as one of the top priorities for exploration in the coming decades. Plans are forming for an orbiter that could launch in the 2030s, using gravity assists from Jupiter to reach the planet by the 2040s. Think about that timeline for a moment. A mission that launches 15 years from now wouldn't even arrive until most of us are middle-aged or older. The scientists designing it now might not even live to see the results. That's what space exploration at this scale means. You work for the next generation's discoveries, not your own. But what could such a mission reveal? For one, Uranus's interior remains a mystery. Its magnetic field could hold clues about how planets generate magnetic dynamos. Its faint, dusty rings, first discovered by accident when a star passed behind the planet in 1977, could tell us how ring systems form and evolve. Its moons, like Miranda, Ariel, and Titania, could turn out to be geologically active, hiding underground oceans or cryovolcanoes that spew ice instead of lava. Voyager's limited data hinted at these possibilities, but without an orbiter to watch them closely, we're left guessing. Imagine being the first spacecraft to return there. As you approach, the pale disk of Uranus grows larger against the black backdrop of space. Sunlight is dim now, less than a quarter as strong as what reaches Earth. The stars don't twinkle here, they pierce. You pass through the planet's faint rings, so delicate they look like whispers of dust suspended in time. The planet's blue-green glow fills your view. It's cold, silent, and endless. The instruments hum quietly as they start scanning the atmosphere, sending back data that takes hours to reach Earth. You're seeing a world no one has truly seen in nearly a century. The idea alone feels almost spiritual, because when you realize how long it takes to reach Uranus, 8, 10, 12 years, you begin to understand that these aren't just scientific missions. They're acts of faith. We launch them, knowing we'll never see the results immediately. We send them into the unknown and trust the future to catch up. That's what Voyager did. It left Earth before many of today's scientists were even born. Yet its legacy still shapes everything we know about the outer planets. And Voyager 2's encounter with Uranus wasn't just scientifically important. It was emotionally profound. During its brief flyby, it discovered 11 new moons, detected 10 new rings, and measured temperatures colder than anywhere else in the solar system. It revealed that Uranus's upper atmosphere was nearly featureless because of its low internal heat. Unlike Jupiter and Saturn, which radiate more heat than they receive, Uranus emits almost nothing. It's as if the planet's internal engine simply shut down. Some scientists think that might also be a result of the same collision that tilted it, a blow that not only knocked it sideways, but also disrupted its core so deeply that it no longer generates significant heat. So while Jupiter burns with storms and Saturn glows with auroras, Uranus just drifts, frozen, silent, a planet that feels less alive and more like a memory. But maybe that's what makes it so haunting. Uranus is the planet of lost potential, the world we saw once and then abandoned, the one that still waits for our return. And when you think about it, that makes Voyager 2's brief visit feel almost poetic. It came, it looked, it left, like a passing ghost waving goodbye. Today, Voyager 2 is still out there, sailing through interstellar space more than 20 billion kilometers away. Its signal grows weaker each year, but it continues to speak to us, whispering data from the edge of the unknown. Somewhere in that endless distance is the memory of the moment it looked back at Uranus, the only human-made witness to that distant rolling world. And here's the thing. Uranus may have been forgotten, but it's not gone. Every few years, astronomers catch subtle changes in its clouds, shifts in its atmosphere, seasonal transformations that hint at life beneath the stillness. Even from billions of kilometers away, it's still alive in its own way, waiting, watching. If it took Voyager 2 8.5 years to reach Uranus with 1970s technology, Imagine what could happen now. With next-generation propulsion, nuclear thermal engines, ion drives, or even fusion concepts, we could cut that time in half. A fast-tracked mission could reach Uranus in 4 or 5 years, and with onboard AI, it could conduct research autonomously, making decisions in real time instead of waiting hours for Earth's instructions. By the time we reach Neptune, we've left the familiar world behind. Neptune, the last known stop. The blue planet sits more than 4.5 billion kilometers from the Sun. That's almost 30 times farther than Earth. Out here, light itself slows down, taking over 4 hours to travel from the Sun to Neptune's skies. Imagine standing on the edge of everything you've ever known, watching a dim golden dot in the distance that was once your home star. That's Neptune, the final destination in our known solar neighborhood. Beyond this, there are only icy shadows and cosmic silence. When Voyager 2 launched in 1977, no one truly knew how long it would take to reach the outermost world. It had already passed Jupiter in 1979, Saturn in 1981, and Uranus in 1986. Each planet revealed more mysteries, more beauty, but Neptune was the crown jewel. After 12 years of flight, Voyager finally reached it in August 1989. 12 years. A human child could be born, learn to walk, talk, and enter middle school, all while a spacecraft silently crossed the dark void toward one target. That's what it took to reach Neptune once, and we've never gone back. To understand how immense this is, picture the solar system as a racetrack. Earth orbits around the 1 kilometer mark. Jupiter sits at about 5 kilometers, Saturn at 10, Uranus at 20. Then, way out past the curve of imagination, Neptune appears at 30 kilometers. The finish line nobody reaches easily. Every meter farther demands exponentially more energy, more time, and more patience. Voyager 2 was moving at an incredible speed, around 15 kilometers per second, faster than any bullet, any aircraft, any object humans had ever built. Yet even at that mind-bending pace, it took 12 years to get there. 12 years to reach the edge of the Sun's influence, where the warmth fades and darkness becomes almost absolute. Now think about what it would mean if you tried to go there today. The fastest rocket humans have ever launched, NASA's Parker Solar Probe, travels at around 700,000 kilometers per hour at its peak. But that's only near the Sun, using its gravity to slingshot faster. If you tried to send that same spacecraft toward Neptune, the story changes completely. The distances are so massive and the energy requirements so high that even with today's top technology, you'd still be looking at a journey of at least a decade. That's the staggering truth of space travel. Even with the best we have, the cosmos barely moves for us. We are toddlers crawling across an infinite floor. And Neptune isn't just far, it's elusive. The planet's orbit is tilted and stretched, meaning its distance from the Sun changes drastically. Sometimes Pluto, which orbits in a more oval path, is actually closer to the Sun than Neptune. It's a strange quirk of cosmic geometry, the kind that reminds you that even our neat diagrams of the solar system are simplifications. Reality out here is messy. When Voyager 2 arrived, the spacecraft captured images of Neptune's deep blue atmosphere, streaked with violent storms and swirling winds faster than any hurricane on Earth. One of those storms, the Great Dark Spot, was so massive it could swallow our entire planet. Yet just 5 years later, when the Hubble Space Telescope looked again, the storm was gone, vanished into the endless gas. Neptune is alive, but in a way that feels alien to us. Its winds blow at 2,000 kilometers per hour, and temperatures hover near -200 degrees Celsius. It's a world of ghosts, where sunlight is 4 billion kilometers away and time seems frozen. But imagine for a moment if humans tried to make that trip. Let's say we launched a crewed mission using current chemical rockets, the kind used by SpaceX or NASA. With those, we could reach Mars in about 6 to 9 months. Jupiter might take around 5 years. Saturn, 7. But Neptune, you'd be staring at 25 to 30 years of travel. And that's being optimistic. A whole generation would grow up and grow old before you arrived. Even if we could keep the crew alive that long, the psychological weight would be immense. There's no resupply, no rescue. Communication signals from Neptune take 4 hours to reach Earth and another 4 hours for the reply to come back. An 8-hour conversation delay for a single question. Are we still on course? 8 hours later. Yes. Every command, every correction, every human word slowed down to the pace of eternity. That's the emotional wall of deep space. You don't just travel through distance, you travel through time itself. Scientists and engineers dream about ways to cut that down. Nuclear propulsion, ion drives, even antimatter engines. They all promise speeds that could transform those decades into mere years. A nuclear thermal rocket, for example, could theoretically get us to Neptune in under 10 years. A fusion-powered craft might do it in 5. But these are all still dreams on paper, ideas waiting for breakthroughs. We're still bound by the physics of fuel, thrust, and gravity. Now let's imagine the impossible, traveling at a fraction of light speed. Light moves at about 300,000 kilometers per second. If you could somehow cruise at just 1% of that, 0.01 CE, you could reach Neptune in about 15 hours. That's faster than a long-haul flight from New York to Sydney. But even at 1% of light speed, you'd need energy equivalent to detonating thousands of nuclear bombs just to accelerate. And slowing down when you arrived? That's an entirely different nightmare. So, in reality, Neptune remains what it has always been. A beautiful, unreachable outpost, the last known stop in the Sun's domain. Standing there, if you could, the Sun would look like a bright star, not a blazing orb like we see from Earth, but a distant light lost in darkness. The warmth you'd feel would be almost non-existent. If you stretched out your hand, the sunlight wouldn't even feel like sunlight anymore. It would feel like cold light, thin and far away. So when we talk about Neptune as the last known stop, it's not just literal. This is where our maps end. Beyond Neptune, there are no missions, no images, no detailed charts, only data, math, and imagination. Out there, the Sun becomes a memory. Out there, we're flying blind. And for all our technology and ambition, we are still at the beginning of space travel. We've touched the Moon, sent robots to Mars, and reached the edge of the solar system, but that edge is still in our cosmic backyard. The galaxy itself, the Milky Way, stretches across 100,000 light-years. Even traveling at light speed, which we can't, it would take 100,000 years to cross it. Neptune, for all its distance, is a tiny pebble on the shore of an infinite ocean, the icy frontier of the Kuiper belt. Beyond the orbit of Neptune begins one of the most mysterious and untouched regions in our cosmic neighborhood, the Kuiper belt. This is where the solar system starts to dissolve into the unknown. It's a vast, frozen wasteland stretching billions of kilometers across, filled with chunks of rock and ice left over from the birth of our Sun. The Kuiper belt begins roughly 30 astronomical units from the Sun. That's 30 times farther than Earth. It extends out to about 50 AU, maybe even farther. 1 astronomical unit, or AU, is the distance from Earth to the Sun, about 150 million kilometers. So the Kuiper belt lies between 4.5 and 7.5 billion kilometers away. But those numbers are almost meaningless until you put them into time. Because that's how space is measured. Not in distance, but in how long it takes to get there. To reach the Kuiper belt, Voyager 2, traveling at over 15 kilometers per second, took more than a decade just to reach Neptune's orbit. Then it kept going. Even now, almost 50 years after its launch, Voyager 2 is just barely crossing the fringes of the Kuiper region. And Voyager 1, its twin, which took a different route, has only recently entered interstellar space after nearly half a century of non-stop travel. That's how vast this region is. If you were on a spacecraft headed that way, you'd see almost nothing. The stars wouldn't move. The Sun would shrink to the size of a bright dot, about as powerful as the Moon seen from Earth. The planets you left behind would no longer be visible to the naked eye. You'd be surrounded by blackness, broken only by the faint shimmer of distant ice worlds reflecting what little sunlight they receive. This is the realm of Pluto, Eris, Haumea, and Makemake, the dwarf planets. They're the silent guardians of the solar system's edge, orbiting slowly through a zone of frozen debris. For decades, astronomers thought Pluto was alone, a strange outcast planet that didn't quite fit with the rest. But when telescopes grew stronger and digital surveys scanned deeper, they discovered the truth. Pluto wasn't an outlier at all. It was just one of thousands. The Kuiper belt is filled with objects like Pluto, some smaller, some even larger. And that changed everything we thought we knew about the solar system. When New Horizons, NASA's small piano-sized spacecraft, launched in 2006, it was on a mission to explore that frozen frontier. After traveling at speeds exceeding 58,000 kilometers per hour, it reached Pluto in 2015. That's nearly 10 years of flight. 10 years just to reach one of the closer Kuiper belt objects. But what it saw when it got there stunned the world. Pluto wasn't just a dead rock. It had mountains of ice, vast plains of nitrogen, and a thin blue atmosphere. It was alive in its own way, dynamic, complex, hauntingly beautiful. From there, New Horizons continued on, deeper into the Kuiper belt, toward another object known as Arakoth, an icy remnant about 6.6 billion kilometers from the Sun. That encounter happened in 2019, making it the farthest flyby in human history. The spacecraft revealed a world shaped like two snowballs gently fused together, untouched for billions of years. Scientists called it a time capsule because it preserved the exact conditions of the early solar system. Every ridge, every curve, every crater was a frozen piece of our origin story. If you think of the solar system as a city, the Kuiper belt is the forgotten outskirts, the quiet neighborhood no one visits, but where all the oldest buildings still stand. The air is thin, the streets are empty, but history lingers everywhere. Out here, the speed of light feels slow. If you were to shine a flashlight toward Earth, it would take almost 6 hours for the beam to get there. Communication from spacecraft is painfully delayed. A signal from New Horizons today takes about 7 hours to reach NASA's antennas on Earth. That means when engineers send a command, even something as simple as turn your camera, they wait nearly 14 hours to know if it worked. There's no room for mistakes. Every instruction must be perfect, every calculation flawless. Space this far out is not forgiving, but it's also not empty. The Kuiper belt is home to trillions of icy fragments, remnants of the primordial disk that once surrounded the newborn sun. Some are as small as pebbles, others are hundreds of kilometers wide. Scientists believe that many comets that visit the inner solar system are born here, shaken loose by the gravity of passing planets or nearby stars. Each one carries clues about the chemistry of early creation: water, carbon, methane, and even complex organic molecules. So when we study the Kuiper belt, we're not just studying cold rocks, we're studying the seeds of life. It's easy to think of the outer solar system as a place of death, frozen, silent, desolate. But in truth, it's the opposite. The Kuiper belt is alive with history, a slow-motion museum of the universe's earliest moments. Everything closer to the sun has been baked, reshaped, or destroyed by heat and gravity. But out here, it's as if time stopped billions of years ago. If a spacecraft could fly fast enough, say 10 times the speed of New Horizons, it would still take about a year just to cross this region. That's how enormous it is. Imagine traveling at 60,000 kilometers per hour, faster than any airplane ever built, for 12 straight months, and still being surrounded by more of the same endless ice. That's the Kuiper belt. There's something deeply humbling about that scale. On Earth, we measure distance in miles or kilometers. In the solar system, we use astronomical units. But beyond Neptune, those units start to lose meaning. Out here, you start thinking in terms of light hours, even light days. You measure your journey not by where you are, but by how long it's been since you last saw sunlight. And when you cross the far end of the Kuiper belt, around 50 AU from the sun, something remarkable happens. the density of objects starts to thin. The ice grows sparse. Space becomes darker, quieter, lonelier. It's as if the solar system itself fades away behind you. You're no longer among the planets, or even the remnants of their creation. You're leaving the sun's dominion. This is where the solar system begins to blur into interstellar space, the realm between stars. Scientists call the next region the scattered disk, a chaotic zone where icy objects move in wildly tilted orbits, stretched by gravitational interactions long ago. Beyond that lies the mysterious Oort cloud, a vast, spherical shell of icy bodies that may extend halfway to the next star. But before we step that far, we linger here, in the frozen frontier, to take one last look at where we came from. The Kuiper belt is not just a border, it's a story, one written in ice and silence. It's the leftover debris of creation, still orbiting after billions of years, still whispering the secrets of how everything began. It's where the solar system keeps its oldest memories. If you were standing on one of its larger bodies, the stars would look brighter and sharper than ever before, because the sun's glare would no longer dominate the sky. The constellations would shimmer like diamond dust on black velvet. You'd feel no wind, no sound, no sense of motion, only the quiet hum of eternity. From that frozen surface, if you looked back toward the sun, you'd see a faint golden point, so small that you could cover it with the tip of your finger. Earth would be invisible, hidden in that speck of light. Every story, every person, every moment of human history, all contained in a single pixel hanging in the dark. That's the perspective the Kuiper belt gives you. It's not just distance, it's humility. And yet, even from here, we're still not far in galactic terms. The Milky Way is 100,000 light-years wide. The Kuiper belt, barely a few light-hours across. It's the first step outside our planetary neighborhood, the beginning of a journey that could someday take us to other stars. New Horizons is still moving deeper into it right now, sending back faint signals, studying more of those frozen relics. And when its power finally runs out, sometime in 2030s, it will keep going, silent but unstoppable, drifting through the darkness for millions of years. It will become one more artifact among the billions out there, a man-made relic among nature's own. The Oort cloud and the edge of home. If the Kuiper belt is the frozen frontier, the Oort cloud is the great cosmic wilderness that lies beyond it. A vast, almost mythical region marking the true edge of our solar system. It's a place so distant that no spacecraft, no telescope, and no human eye has ever seen it directly. It exists only through math, gravitational evidence, and the faint whispers of icy travelers that sometimes fall from its depths. The long-period comets that blaze across our sky for a brief moment before vanishing again into eternity. This is the solar system's final veil, the edge of home. To understand what that means, imagine standing on the outermost rock of the Kuiper belt, watching the sun shrink until it looks no brighter than any other star. Behind you stretches a black ocean that goes on for nearly 2 light-years. That's almost 20 trillion kilometers, filled with countless icy fragments drifting in darkness. That is the Oort cloud, the largest structure belonging to the sun. It's not a ring or a belt like the ones closer in. It's a sphere, a bubble surrounding our entire solar system like a frozen halo. No one knows exactly where it begins. Scientists estimate it starts somewhere around 2,000 astronomical units from the sun. That's 2,000 times the distance from Earth to the sun. It might stretch all the way out to 100,000 AU. To put that in human terms, if Earth were 1 meter away from the sun, the Oort cloud would begin 2 kilometers away and extend another 100 kilometers beyond that. It's so unimaginably large that if you could fly through it at the speed of Voyager 1, the fastest human-made object currently leaving the solar system, it would still take you about 300 years just to exit. 300 years. That means Voyager 1, which left Earth in 1977 and has been traveling at over 17 kilometers per second, for nearly half a century, won't leave the Oort cloud until sometime around the year 26,000. That's not a typo, the 26th millennium. By then, every city, every language, every culture that exists today will be ancient history. Civilizations will have risen and fallen. Humanity might live on other worlds or might not exist at all, yet that tiny probe built by humans in the late 20th century will still be drifting silently through the farthest reaches of the Sun's domain. That's how vast the Oort cloud is. It bends time itself. But before we dive too deep into the immensity of it, let's rewind a bit. The Oort cloud is named after Jan Oort, a Dutch astronomer who, in 1950, proposed its existence to explain a mystery that had baffled scientists for centuries. Comets. Comets appear suddenly in our sky, burning bright tails as they approach the Sun. But their orbits often don't fit with the rest of the solar system. Some come from strange angles, not from the plane where the planets orbit. Others don't return for tens of thousands of years or ever. Oort realized that these icy visitors must come from a distant, spherical shell of debris surrounding the solar system, a place where ancient chunks of rock and ice have lingered since the formation of the Sun, occasionally disturbed by passing stars or galactic tides that send them hurtling inward. So in essence, the Oort cloud is the Sun's farthest family, billions, maybe trillions of icy bodies bound so loosely by gravity that they're almost part of interstellar space already. It's the halfway point between ours and theirs. If you could somehow stand on one of those distant objects, an icy world the size of a mountain, orbiting tens of thousands of AU away, you wouldn't see the Sun as a disk. It would look like just another star among billions. The warmth that sustains life on Earth wouldn't even reach you. The space between the particles in your body would be colder than anything we can replicate on Earth. You'd be surrounded by a silence so complete it would almost hum in your ears. The nearest object to you could be millions of kilometers away, moving so slowly that it might take thousands of years just to shift across the sky. And yet this region is still part of the solar system. It still belongs in the loosest sense to the Sun. Its particles are still faintly tethered to our star's gravity. Beyond this, that tether finally snaps, and interstellar space truly begins. When Voyager 1 crossed what's called the heliopause in 2012, the boundary where the solar wind stops pushing against the interstellar medium, scientists said it had entered interstellar space. And that's true, in a sense. But it hasn't yet escaped the Oort cloud. Not even close. It's still in the outskirts of the Sun's influence, still a prisoner of its gravity, though the leash grows weaker every day. Voyager 2, following a slightly different path, is only a few billion kilometers behind. Both are still whispering faint signals home, powered by the slow decay of their nuclear batteries. Each transmission takes over 22 hours to reach Earth. That means every time we talk to Voyager 1, the message travels nearly the entire width of our solar system just to arrive. And every time it answers, that signal spends almost another day on its way back. The spacecraft are so far that the light from the Sun, the fastest thing in the universe, takes more than 20 hours to reach them. Out here, time and distance start to lose meaning. You don't measure your trip in kilometers anymore. You measure it in years of light, in lifetimes. Think about that. The Oort cloud might stretch halfway to the next nearest star, Proxima Centauri. And yet, even at these distances, the Sun still holds on. Its gravity is weak, but not gone. The boundary of the solar system isn't a wall. It's a fading gradient, a slow handoff from the Sun's dominance to the quiet pull of the galaxy beyond. Every once in a while, a passing star or a ripple in the Milky Way's gravitational field nudges one of the Oort cloud's icy bodies out of its orbit. That's how we get long-period comets, objects that take tens of thousands or even millions of years to complete a single orbit. They fall inward, gaining speed as they dive toward the Sun, then loop around and vanish back into the dark, not to return for eons. Each one is a messenger from the edge of home, carrying material untouched since the solar system was born. If you were to watch one of these comets from a ship in the Oort cloud, it would look like a spark lighting up the black. Slowly, almost imperceptibly, it would begin to glow as it neared the faint light of the sun. For thousands of years, it would travel alone through the darkness, until, for a brief few months, it blazed across Earth's skies. Then, as quickly as it appeared, it would vanish again into the abyss. That's the rhythm of the Oort cloud, centuries of stillness, moments of motion. It's the quiet heartbeat of the solar system. So what would it actually take to reach this place? Let's imagine launching a spacecraft right now, say, using the fastest rocket ever built. The Parker Solar Probe, at its peak, travels at about 700,000 kilometers per hour. If it could somehow maintain that speed on a straight path away from the Sun, it would take nearly 800 years to reach the outer edge of the Oort cloud. That's almost a millennium of travel. To send a human crew would be impossible with today's technology. Generations would live and die aboard the ship before it ever reached the boundary. Even if we developed a nuclear propulsion system capable of 10 times that speed, something humanity might achieve in the next century, it would still take nearly 80 years to exit the Oort cloud. And at 1% the speed of light, which is currently far beyond our reach, it would still be a multi-year journey. The scale of this region defies imagination. It makes even the most advanced engineering seem like the slow crawl of an ant across a football field. And yet, even knowing all that, the Oort cloud represents something deeply personal to us as a species. It's the last place we can still call ours. Beyond it, we enter true interstellar space, the ocean between stars, where the sun's gravity no longer defines the map. The moment Voyager 1 finally leaves the Oort cloud, centuries from now, will mark the first time a human-made object officially exits the solar system. That's the moment we'll truly become an interstellar species, even if we're not there to witness it. What's haunting is how small that first step will be compared to the galaxy beyond. Once outside the Oort cloud, the nearest star, Proxima Centauri, will still be 4.2 light-years away, more than 260,000 times farther than the distance from the Sun to Earth. Even traveling at Voyager's incredible speed, it would take over 75,000 years to reach it. Traveling across the Milky Way. And if the solar system were the size of a coin, the Milky Way would be larger than the entire continent of North America. It stretches about 100,000 light-years across, meaning that even if you could travel at the speed of light, it would still take you 100,000 years to cross from one edge to the other. And remember, nothing we can build, no rocket, no probe, not even the fastest theoretical engine, can go anywhere near that fast. The Milky Way isn't a solid disk. It's a swirling spiral galaxy, like a vast cosmic pinwheel made of stars, gas, dust, and dark matter. It has 4 main arms curling outward from a bright central core: the Perseus arm, the Sagittarius arm, the Centaurus arm, and the outer arm. Between them lie smaller spurs and bridges, tendrils of starlight where new stars are born and ancient ones die. At its center lies something extraordinary and terrifying, a supermassive black hole known as Sagittarius A star. It's about 4 million times the mass of the Sun, and it's the gravitational anchor of the entire galaxy. Everything you can see in the night sky, every star and planet, orbits that invisible heart. Earth, and our Sun with it, sits quietly about 26,000 light-years away from the galactic center, tucked inside a minor branch called the Orion Arm, a kind of suburban lane between the larger spiral highways of stars. It's not too close to the chaos of the core, where radiation would fry any chance of life. And it's not too far out, where there wouldn't be enough heavy elements to form planets. In other words, we live in the galactic Goldilocks zone. If you could zoom out far enough to see it all, if your eyes could somehow take in the entire disk at once, you'd see that Earth occupies an almost meaningless dot on a spiral arm halfway out. A single pixel in a galaxy with more than 200 billion stars. And yet, from that pixel, we've mapped the rest of it using light, gravity, and time. We know where we are, but we've never been anywhere beyond our neighborhood. Every map of the Milky Way is built not from travel, but from observation, from photons that have taken thousands, even millions of years to reach us. We see the galaxy as it once was, not as it is now. The light from the far side of the Milky Way began its journey before humans even existed. If the solar system feels enormous, the Milky Way makes it feel microscopic. Our fastest probes, Voyager, New Horizons, Parker Solar, would take hundreds of millions of years to reach the galactic edge. We could launch 1,000 more tomorrow, and they'd all still be crawling at the scale of galactic time, and yet we still dream about crossing it. From Earth, the galactic center lies in the direction of the constellation Sagittarius, hidden behind thick clouds of interstellar dust. You can't see it with your eyes, but if you could look through that haze, through tens of thousands of light-years of space, you'd see a bright, crowded region bursting with stars, nebulae, and radiation. And right at the middle, like an eye surrounded by light, is Sagittarius, a star. The distance from Earth to Sagittarius. A star is roughly 26,000 light-years. That's about 2.5 x 1017 kilometers, a number so large it defies comprehension. Even at the speed of light, 300,000 kilometers per second, it would take 26,000 years to get there. That means, if you left today, traveling at light speed, Earth's continents would have shifted. Languages would have evolved into something unrecognizable, and the sun itself would be entering middle age by the time your descendants arrived. But of course, nothing with mass can actually reach light speed. Einstein's theory of relativity forbids it, because as you approach light speed, your mass effectively becomes infinite, and so does the energy needed to keep accelerating. In other words, to move that fast, you'd need infinite energy, and infinite energy doesn't exist. So we're forced to imagine slower but still astonishing alternatives. If we could travel at 1% the speed of light, the trip would take 2.6 million years. At 10%, it drops to 260,000 years. Even at 50%, the best-case fantasy, we're still talking 52,000 years to reach the core. Those numbers feel almost cruel, even at half the speed of light, something no technology on Earth is remotely close to. The trip would take 10 times longer than the entire history of human civilization. But what if we didn't move through space the usual way? What if we could bend it instead? This is where theory collides with imagination and gives birth to ideas like the Alcubierre drive, named after Mexican physicist Miguel Alcubierre, who proposed it in 1994. The concept comes straight from Einstein's general relativity equations. Instead of pushing a ship through space, the Alcubierre drive would warp space-time itself, compressing it in front of the ship and expanding it behind, creating a bubble that rides the wave of warped space. Inside the bubble, the ship itself never moves faster than light. But the bubble, the distortion of space, can move as fast as it wants. To an outside observer, it would appear as if the ship were traveling faster than light. It's a wild, beautiful idea. But it has one massive problem: energy. To create and maintain the warp bubble, the Alcubierre drive would require a form of negative energy, something that doesn't exist in nature, at least not in quantities we can harness. Some theories suggest it could be created through exotic quantum effects like Casimir energy. But even if that were possible, the amount required would be astronomical. One calculation found that warping a bubble just 10 meters across would take more energy than the entire mass of Jupiter converted into pure energy. In other words, we can write it on paper, but we can't build it. Not yet, and maybe not ever. Still, the dream won't die, because it's the only concept we have that might one day make intergalactic travel possible within a lifetime. And if history tells us anything, it's that human curiosity has a habit of turning the impossible into the inevitable, given enough time. If we ever did manage to travel to the galactic center, what would we find? The view would be unlike anything seen before. Stars would crowd the sky so tightly that night would be a soft, endless glow. The density of stars near Sagittarius. A asterisk is millions of times greater than in our region of the galaxy. Giant blue supergiants, red hypergiants, neutron stars and pulsars would all coexist, orbiting the black hole in complex, violent paths. And then there's Sagittarius A star. It's not a hole in the sense of a pit. It's an object with gravity so strong that even light can't escape it. Surrounding it is a swirling disk of gas and dust, moving at nearly light speed, glowing with X-rays and radio waves as it falls inward. The Event Horizon Telescope gave us our first ever image of it in 2022. A blurry orange ring surrounding a shadow, proof that we were finally seeing the unseeable. The gravitational pull would stretch and tear anything that got too close, shredding it atom by atom, a process scientists call spaghettification. Time itself would slow down near the event horizon. To an outside observer, you'd appear frozen forever at the edge, never quite falling in. But imagine the courage it would take to go there, to stand on the deck of a starship, staring out into a sky where every direction burns with light, and in the center, the ultimate abyss, glowing faintly like an eye staring back. The heart of the galaxy, the end and the beginning of everything we know. Even if we could never survive the journey, the idea of it humbles us, because every single star, planet, and particle in the Milky Way is caught in that black hole's gravity. It's what holds us all together. In a way, Sagittarius, a star, is the galaxy's heartbeat, slow, steady, eternal. We orbit it without realizing it. Every sunrise, every night sky, every spinning planet, all of it moves in that invisible rhythm, completing one full orbit every 230 million years. The last time our solar system was on this side of the galaxy, dinosaurs walked the Earth. By the time we circle back, who knows what we'll have become? From the outside, our galaxy might look calm, a quiet spiral drifting in space. But inside, it's alive, pulsing with energy, storms, collisions, and gravity so intense it can shape the future of everything within it. And there we are, halfway out on one of its arms, dreaming about the day we might finally cross it. The Milky Way isn't just our home, it's our universe within a universe. A colossal city of stars, where every light in the night sky is another sun, and every sun holds the possibility of new worlds, new stories, new beginnings. And even though we may never live long enough to see its heart up close, just knowing it's there, just knowing what lies at the center of our spiral, changes how we see everything else. If you could stand on the outer rim of the Milky Way and look inward, the galaxy would appear like a massive glowing whirlpool, bright streams of stars and gas twisting in elegant spirals around a dense, glowing core, crossing the spiral arms. But the moment you tried to cross it, the illusion of closeness would break. From afar, the spiral arms look almost painted together, like rivers of light blending at the edges. Up close, they are separated by incomprehensible gulfs, each star system spaced apart by light years of nothingness. Every one of those stars could have planets. Some might be warm and blue, others icy and dim, some shrouded in dust. But as you chart a path through the spiral arms, you quickly realize the problem isn't finding destinations, it's reaching them. Between even the nearest systems, the average distance is about 5 light-years. That's around 47 trillion kilometers. To put that in perspective, if you could somehow drive your car at highway speed, say 100 kilometers per h, it would take over 500 billion years to make the trip. The universe doesn't care about our sense of scale. It operates in magnitudes that laugh at our engines, rockets, and lifetimes. Let's imagine, though, that humanity has made it this far. We've already passed through the inner solar system, left Neptune behind, drifted through the Oort cloud, and crossed into true interstellar space. Our ship now moves not in kilometers per hour, but in fractions of the speed of light, maybe 10%, maybe 20%. Even at that speed, it would take decades to hop from one star to another. That's how enormous the Milky Way's spiral arms are, Each arm, like our own Orion arm, spans thousands of light years in length and hundreds of light years in thickness. Moving across it isn't like traveling between cities. It's like trying to walk across an ocean of stars, one light-year step at a time. Now imagine planning a galactic road trip. You'd start with a map, not of roads, but of routes through gravitational currents, star clusters, and stable regions of interstellar gas. Just like pilots on Earth avoid turbulence, deep space navigators would need to avoid dense nebulae or high radiation zones. The first stop might be Proxima Centauri, a humble red dwarf, then Barnard's star, about 6 light-years away. From there, you might jump toward Wolf 359, a dim ember of a sun in the direction of Leo. That leg alone would take more than 50 years at 10% light speed. You wouldn't travel in a straight line either. The Milky Way's arms are constantly rotating, but not like a solid wheel. The inner regions spin faster than the outer ones, meaning that by the time you've crossed even a small segment, the galaxy has twisted around you. The stars you left behind are no longer where you remember them. The galactic map keeps shifting, a cosmic GPS where even light takes thousands of years to update the screen. Between the arms lie even greater voids, interarm regions, deserts of space where the nearest star may be tens of light years away. Crossing those would be the longest, loneliest stretches of the journey. Out there, you'd see fewer and fewer points of light. The night sky would darken, constellations fading into a backdrop of endless black. Even radio signals from home would take centuries to catch up, long after their senders were gone. And yet, traveling across the spiral arms would tell the story of our galaxy itself. Each arm is not just a structure, it's a timeline. The inner arms are older, filled with ancient red stars nearing the end of their lives. The outer arms, including ours, are younger and richer in gas, full of stellar nurseries where new suns are being born. If you could cross from one arm to another, you'd literally be moving through eras of cosmic history, from old, quiet neighborhoods to vibrant regions buzzing with newborn light. The Orion arm, where Earth lives, is just a minor spur tucked between two major arms, Sagittarius and Perseus. Our little region is only about 3,500 light-years wide, but it's our home. To cross just this segment, even at light speed, would take thousands of years. That's the scale we're dealing with. You could travel faster than anything imaginable and still spend entire human civilizations just moving between arms of the same galaxy. Of course, scientists have theorized how we might one day cut that time down. Warp drives, if ever made real, could distort space-time itself, compressing the distance ahead and expanding it behind, letting you surf the fabric of the universe. In theory, a warp bubble could move faster than light without violating physics locally. But the energy required would be almost impossible to achieve. You'd need the equivalent of all the mass in Jupiter, converted into pure energy, just to move a small ship a few light years. It's mind-breaking to even imagine. But if it were possible, the Milky Way would suddenly feel smaller. You could cross from one spiral arm to the next in months instead of millennia. Human exploration could reach the galactic center, visit nebulae, and map regions where black holes silently feed. Civilization could spread across thousands of worlds, connected not by radio, but by ships that arrive before their messages. Yet that's still science fiction, for now. The truth remains that our galaxy is immense beyond human comprehension. Even our fastest probes, like Voyager 1, are barely a tenth of a light day away from Earth after nearly 50 years of travel. They haven't even reached the nearest interstellar dust cloud, let alone another star. Crossing the Milky Way's spiral arms with today's technology is like trying to cross the Atlantic in a paper boat. Still, the dream persists. We keep sending ships, signals, and stories into the void, whispers across the spiral arms. Because one day someone, or something, might answer back. And when that day comes, we'll finally have proof that we're not alone in this enormous spiraling ocean of stars. From here, the path only grows longer. Past the spiral arms lies the heart of the galaxy, the blazing turbulent region around Sagittarius A*, a supermassive black hole pulling everything toward its invisible grip. Traveling there isn't just a question of distance anymore. It's a journey into the most extreme forces in the known universe. And for any traveler daring enough to try, crossing the arms is only the beginning of what it truly means to move across the Milky Way. Far edge of the galaxy. The impossible journey. At the very edge of the Milky Way, toward the glowing core, that blinding swirl of stars and dust some 50,000 light-years away in either direction, is a titanic spiral 100,000 light-years across, glittering like a whirlpool of diamonds frozen in motion. Every single point of light is a sun, some brighter than our own, some dimmer, and many orbited by planets we'll likely never reach. That's the scale of home, our galaxy, one of billions. And crossing it is one of the most unimaginable journeys in existence. Let's talk numbers first, but in a way that really hits. The Milky Way is roughly 100,000 light-years wide. That means, if you could somehow ride a beam of light, the fastest thing in the universe, it would still take you 100,000 years to travel from one edge to the other. 100,000 years ago, humanity was still using stone tools, painting in caves, and learning to survive ice ages. So if light had left the other side of the galaxy back then, it would just now be arriving here. Now, here's where it gets even wilder. Our fastest spacecraft, Voyager 1, launched in 1977, is currently traveling at about 17 kilometers per second. It's the farthest man-made object from Earth, more than 24 billion kilometers away. That sounds incredible, until you realize it's still within the sun's gravitational influence and hasn't even fully exited the Oort cloud yet. If Voyager kept going at its current speed and aimed straight across the Milky Way, it would take around 2 billion years to make it to the far edge. 2 billion years. That's almost half the age of the Earth itself. In other words, even with all our technological brilliance, we haven't even made the first baby step. At the scale of the galaxy, we're still in our cosmic backyard, more like toddlers crawling on the living room floor while the rest of the house stretches into infinity. And yet, there's a haunting beauty in that realization. The Milky Way's edge isn't just far. It's conceptually impossible with what we have now. But that hasn't stopped us from trying to reach, to touch, to send something, anything, that carries our story into that endless dark. When Voyager 1 and its twin Voyager 2 were launched, they were equipped with something remarkable, the Golden Record. It's a 12-inch gold-plated copper disc containing sounds, music, and images from Earth. Greetings in 55 languages, the sound of waves, thunder, a baby crying, and even Chuck Berry's Johnny Be Good. It's our time capsule, drifting through the void, carrying proof that we once existed, that we reached out and said, we were here. That record will still be out there long after we're gone, perhaps for 1 billion years or more. By the time it reaches another star system, humanity as we know it might have evolved, gone extinct, or become something entirely unrecognizable. The odds of it ever being found are infinitesimally small. Yet, it remains our most ambitious message, not meant for contact, but for meaning. The farthest intentional message we've ever sent is another kind of beacon, the Arecibo message, transmitted from Puerto Rico in 1974. It was a simple 1,679-bit binary signal, encoded with information about human DNA, our solar system, and a basic image of the human figure. It was aimed at a star cluster 25,000 light-years away, M13, in the constellation Hercules. If it ever gets there, it'll arrive in the year 26,000 AD. That's not science fiction. That's just how space works. Even at the speed of light, communication across the galaxy takes longer than the entire span of human civilization so far. So how could we ever go there, to the far edge of the Milky Way itself? Not with humans, at least not yet. Our fragile biology isn't built for centuries or millennia of travel. Radiation, isolation, and sheer time would destroy us long before we made it halfway. But artificial intelligence, that might just be our key. Imagine self-replicating AI probes, machines that can repair themselves, build copies of themselves from materials found along the way, and continue the mission indefinitely. These von Neumann probes, as theorized by scientists, wouldn't need food, sleep, or oxygen. They could move slowly, even at a fraction of light speed, and still succeed, because they don't measure time the way we do. A few thousand years to them is nothing. Each probe could spread out, hopscotching from one star to the next, mapping the galaxy like cosmic breadcrumbs. Eventually, they could create a digital network spanning the Milky Way, a kind of galactic internet linking every reachable system. Humanity, even if long gone, would have its legacy preserved and spread across the stars through machines that carry our knowledge, our art, our history. But even that isn't simple. Space between stars isn't empty. It's filled with dust, debris, and radiation that would batter any traveling object over millions of years. The energy requirements to accelerate even a small probe to near-light speeds are staggering. To send a 1-ton probe at just 10%, the speed of light, would take more energy than humanity currently produces in a year. Still, technology keeps evolving. Projects like Breakthrough Starshot are already experimenting with miniature light sail probes that could, theoretically, reach nearby stars within a human lifetime, propelled not by rockets, but by powerful lasers from Earth. Imagine scaling that idea up. An armada of light sails fanning out from the solar system, each heading toward a different corner of the galaxy. They drift for centuries, then millennia, sending back data as they go. One day, perhaps, those tiny machines, or their descendants, might see the Milky Way's far edge with their own sensors. They might turn back toward home and send a faint, almost ghostly image. The galaxy as a whole, glowing softly in the black, with a tiny arrow pointing to a small dot halfway in. You are here. And that's what makes the thought of the galaxy's far edge so powerful. It's not just distance, it's destiny. The farther we imagine going, the more we understand about what we are, creatures built to look outward, to wonder, to chase horizons we'll never reach. If Voyager takes 2 billion years to make it there, that means it will make it eventually. It'll drift, untouched, unseen, through generations of stars being born and dying, through the slow evolution of the galaxy itself. Long after the sun burns out, Voyager will still be moving, a tiny spark of human curiosity outliving its creators by eons. Maybe someday a distant civilization will catch it, examine it, and realize what it is. They'll see the golden record, decode our greetings, hear the laughter of children, and listen to the heartbeat of a woman recorded in 1977. And for a brief moment, they'll know that somewhere, sometime, there were beings who looked up and dared to cross the impossible. Reaching the far edge of the galaxy may be beyond us, but sending a piece of ourselves, a story, a signal, a symbol, that's something we've already done. We may never walk the other side of the Milky Way, but in a way, we've already touched it. The impossible journey has already begun, not through bodies or ships, but through the echoes of everything we've sent into the stars. The concept of time in deep space. You see, time, as we live it on Earth, feels fixed. It's the steady rhythm of sunrise and sunset. Clocks ticking, calendars turning. But once you leave the planet, once you step beyond the pull of gravity and begin moving through the void at immense speeds, time stops behaving the way we expect. It stretches, bends, slows. The deeper you go into space, and the faster you move, the more you begin to realize something profound. Time isn't universal. It's personal. It's relative. Imagine for a second that you're aboard a spaceship capable of near light speed travel. To you, inside the ship, everything feels normal. Seconds tick by on your watch, meals come and go, you age the same way you always have. But from Earth's perspective, you've entered a different reality. As your ship approaches the speed of light, time for you slows down relative to those watching from home. Hours for you could be years for them. This isn't science fiction. It's Einstein's theory of relativity, and it's been proven again and again through real-world physics. To understand why this happens, you have to think of time and space as a single thing, space-time. According to Einstein, the faster you move through space, the slower you move through time. It's like there's a balance the universe keeps. You can't move quickly through both at once. So if your ship is racing through space at near light speed, it's sacrificing its movement through time, meaning you're aging slower. That's called time dilation, and it's one of the strangest, most mind-bending effects in physics. Let's make it concrete. If you traveled to Proxima Centauri, the nearest star to Earth, at 99.9% of the speed of light, the trip would take a little over 4 years from Earth's point of view. But inside your ship, you'd only experience a few months. When you came back home, you'd find that nearly a decade had passed on Earth, while you had only aged a fraction of that. Now push it further. If you could somehow travel to the galactic center, about 26,000 light-years away, at the same speed, you'd see the whole Milky Way flash by in what might feel like hours or days. But when you arrived, if you ever could, tens of thousands of years would have passed on Earth. Civilizations would have risen and fallen, languages would have evolved, humanity might not even exist anymore. You'd return a stranger to a planet that no longer remembers you. That's the paradox of deep space travel. The faster you go, the less of the universe you personally experience. You could cross impossible distances, but everything you left behind would age into oblivion. For the traveler, time becomes mercifully short. For everyone else, it becomes endlessly long. This isn't just theory, we've actually observed it. Astronauts aboard the International Space Station experience time dilation every single day. Because they're orbiting Earth at about 28,000 kilometers per hour, they age slightly slower than people on the ground. It's a difference of milliseconds, but it's measurable. In fact, the most precise atomic clocks ever built show that even being a few feet higher, farther from the center of Earth's gravity, causes time to run a little faster. Time literally ticks differently, depending on where you are and how you move. But in deep space, those tiny differences turn into centuries. If we ever build ships capable of reaching even 10% of light speed, an incredible feat already, time would already begin to shift. The clocks on board would slowly desynchronize from those on Earth. A 10-year voyage from the crew's perspective might be 12 or 15 years back home. Push the speed to half the speed of light, and the gap widens drastically. By the time you reach 90%, Earth's clocks would be racing far ahead of yours. So what does travel time even mean in a universe like that? If you can get somewhere faster by slowing your own experience of time, have you really arrived sooner? Or have you just stepped outside of everyone else's reality? The truth is, time in deep space stops being a shared experience. It becomes fractured, dependent on perspective. That's why physicists say the universe has no universal now. What's happening right now in another star system could depend entirely on where you're observing it from and how fast you're moving. There's no single cosmic clock keeping time for everyone. If that sounds confusing, imagine two twins. One stays on Earth, the other boards a near light-speed ship and leaves for a distant star. This is the famous twin paradox. The traveling twins' clock slows down, their body ages slower, and when they return decades later, they're younger than their sibling. Both experience time normally in their own frame, but one lived fewer years than the other. That's not just a theory, it's a measurable consequence of relativity. Time isn't fixed to the universe, it's fixed to you. But there's another factor that distorts time, just as powerful as speed: gravity. The stronger the gravitational field you're in, the slower time passes. That's why near a massive body like Jupiter, or even more so near a black hole, time literally drags. For example, near the event horizon of a black hole, where gravity is so intense that even light can't escape, time almost stops relative to the outside world. You could orbit a black hole for an hour, only to return and find centuries have passed elsewhere. Christopher Nolan's Interstellar famously illustrated this with the planet Miller's World, orbiting close to a black hole called Gargantua. On that planet, 1 hour equals 7 years back home. That wasn't just movie magic. It was based on real physics. The combination of gravity and speed bends time so severely that the two travelers and their mission control exist in almost separate timelines. So, when scientists talk about how long it takes to get somewhere in space, there's always a hidden asterisk. It depends on who's asking. For the people on the ship, the journey might be tolerable. A few years, maybe a few decades. For those watching from Earth, it might be thousands. That's why, when we talk about interstellar missions or traveling across the Milky Way, we often switch to describing distance in light years. Not kilometers, not miles. Because time and space have merged into one inseparable thing. There's also the psychological side of it. If time stretches differently depending on your velocity, what does the present even mean for a traveler? Imagine leaving Earth and knowing that everyone you love will age and die while you remain young. The world would keep spinning, generations would pass, entire epochs would unfold, but for you, it would all feel like a handful of years. You'd never truly go home, not because you couldn't, but because home would no longer exist in your timeline. This creates a haunting vision of what deep space travel would really mean. We often imagine it as a grand adventure, crossing galaxies, discovering new worlds, exploring the unknown. But the true cost might not be danger or distance. It might be time itself. The farther and faster you go, the more you become untethered from the human story. You'd become a ghost of time, someone who can move forward but never back. That's one reason some scientists propose generation ships instead, enormous vessels carrying entire populations that live, die, and are replaced over centuries of travel. Instead of bending time, humanity would simply accept it, adapting to the slowness of the universe rather than trying to outrun it. Every generation would be born knowing they'll never reach the destination, but that their descendants will. It's a beautiful, tragic idea. Trading time for continuity, giving meaning to the endlessness of space. But if relativity ever truly becomes part of human travel, then the concept of arrival will change forever. A trip to the nearest star could mean leaving everything you know behind, not in distance, but in time. You could depart 1 century and return to a planet centuries older, a place shaped by descendants who see you as a relic from the past. And yet perhaps that's the most powerful lesson the cosmos gives us. Time is not a wall. It's elastic, flexible, and deeply tied to where you stand and how you move. On Earth, we measure it in clocks and calendars. In deep space, time becomes personal, a fluid experience that bends to your journey. Maybe that's why space fascinates us so deeply. It's not just about distance, it's about the mystery of time itself. How fragile, subjective, and astonishingly complex it becomes when we dare to leave home. Out there, beyond the planets and stars, you don't just travel through space, you travel through time, and that changes everything.